Okay, so in this video I'm going to be recording the 2020 Exam 2 solutions for the VCAA exam paper. 2020 was obviously an unusual year around the world, and because of all the lockdowns, it was actually an adjusted study design in 2020. So there was a lot less probability in 2020, and so this exam contains a lot less of the probability that would have been in a usual exam for the study design at this particular time. And so to that end, this perhaps gives you, this paper is perhaps, got some nice practice questions, but it's not a good representation of what you would see in a normal year. It's an exam 2, so we have use of a CAS calculator, which I've got set up here for me to use, and you would have use of a bound reference. It's a 2-hour exam paper, 2 sections, 20 multiple choice questions in section A and 5 extended answer questions in section B. Okay, let's get started. So we have the multiple choice. All right, let's get going. So let f and g be functions such that, okay, so we've got essentially a whole lot of points on f and g, and the value of g of f of -1 is. Okay, so this is just working through composite functions. So g of f of -1, okay, so obviously f of -1 is equal to 4, okay, so therefore this is the same as g of 4, and then we've been given, sorry, I just changed the colour here, we've been given that g of 4 is equal to 6, and so therefore that will equal 6, and so option D. Let p of x be a cubic polynomial. A, as we've got an unknown coefficient there, it's a real number. When p is divided by x plus 2, the remainder is 5. Okay, so this is just a straight remainder theorem question, fairly standard year 11 sort of question. So if we get a remainder of 5 when we divide by x plus 2, that's because p of -2 is equal to 5. Okay, so we solve that equal to 0. X equals -2. That's what you then solve into your polynomial to work out the remainder. So p of -2 will be -2 cubed minus 2 times a times -2 squared plus -2 minus 1, and that has to equal 5. And so we're just solving for a. So we could use our CAS obviously to help us here. We could have defined the function and then solved p of -2 equals 5. But to be honest, this is, I think, more efficient by hand if you've got reasonable number skills. So -8, -2 all squared is +4, so times -2 is -8a, and then we've got -2 and -1. All right, so we've got -8a minus 11 equals 5. And so adding 11, -8a equals 16, and so a is going to be -2, so option E. Okay, question 3. Let f dash x be this. If f of 6 equals 4, then. Okay, so we've got the derivative and a point, and we want to find the original function. So we're going to anti-differentiate the derivative to get the original function. So f of x is the antiderivative of the derivative. So that is the antiderivative. I'm going to write that as 2 times 2x minus 3 to the -half. The other thing, of course, that we have access to in in both exam papers is the formula sheet. So if we're going to integrate this by hand, which, if you know your rules, it's probably quicker to do by hand, we'd be looking at this particular rule here. So we've got an ax plus b to the n, where our n is -half. So as long as n is not -1, this rule applies. So we can use that there. So obviously we're going to have 1 on a times n plus 1, and then it'll just be whatever's in our bracket to the power of n plus 1. Okay, so if I go back over here, again, I could get my CAS to do this if I wanted to, but by the time I type it in, sometimes things aren't as quick. So we're dividing by a, which in this case is 2, and we're dividing by n plus 1, so n is the power. Adding 1 to that gives us +1/2. And then we're going to have, 2x minus 3 to the +1/2. Sorry, it's not a definite integral, so I don't need those. We're going to have a plus c though, because it's not a definite integral. Okay, so that's just going to be 2 times square root of 2x minus 3 plus c. All Right, so we've got our point f of 6, which would mean 2 times the square root of 12 minus 3, so that's 9, plus c equals 4, and so that's going to be 6 plus c equals 4, and so c is negative 2. And so therefore our equation is going to be, if we put negative 2 back in up there, we're going to have 2 times the square root of 2x minus 3 minus 2, and so that's going to be option C. Okay, question 4. The solutions of this equation are, okay, so we could probably use our CAS to solve this, making sure we're in radian mode. Obviously, we can see, unless it specifies the solutions are in degrees, they're always going to be in radians. That's the default units. Also, all the pi's in the solution tells us we're in radians, so just making sure your CAS is in the right mode. So up the top here, you can see it says radians. I could just click on that to change it to degrees, so change it back to radians. So we're going to solve. Now, I expect when I solve this, it's not going to give me an answer that looks exactly like the multiple choice options. That would be a really trivial question for them to ask. So we might have to do a bit of work once we get there. And to some extent, that sometimes means that you actually would have got closer to one of their answers by doing it by hand. So sometimes there's a good trade-off for that as well. But this one's a bit messy. There's a lot going on in this cos equation. Okay, so 2 times cos of 2x minus pi on 3 plus 1 equals 0. Solving that for x, we want a general solution, so no domain restriction. Okay, so my CAS gives me this. It actually probably is reasonably similar to what I've got. So we've got pi on 6 times 6n minus 1. So pi on 6 times 6k minus 1 seems to match with both of these. Sorry, both of those. And then the other one is pi on 2. Now see, this is where things are going to be a bit different, isn't it? Pi on 2 times 2x plus 1. Okay, so that's not going to give me, that doesn't match what we've got happening here. So we might need to think about, actually we can see here, if we expand things out a little bit here, oh look, actually there's a common factor here. If we look at that one, there's a common factor of 3 there. So if we divide both the top and the bottom by 3 there, that's going to give us pi times 2k plus 1 all over 2, which does match what we've got. So that will usually be what happens. It's not going to be just a straightforward, you punch in your CAS, you hit solve, the answer is going to match the multiple choice options. You're going to have to do a bit of work to get what the CAS shows you to match what the options are there. So if we just notice that common factor of 3 in there, by dividing everything by 3, we actually get what it shows us on the CAS. So option D here at question 4. Okay, question 5. The graph of this function where D is maximal domain has asymptotes at, okay, so we can certainly get the x asymptote because the vertical asymptote is going to be the value that makes the denominator of the fraction equal to 0. So denominator can't equal 0, which means that x can't equal 5, and so therefore that's why we get an asymptote at x equals 5. So it's definitely going to be one of D or E. And then we could do a couple of different things here. You could get your CAS to sketch it for you. I just really want to get this actually in a more standard hyperbola format, and I can do that by hand, but I could actually get my CAS to help me with this. So if I just do menu, now you can either go through the number or algebra menus, you get the same tools, fraction tools. And if I write this as a proper fraction, so proper fractions are where the numerator is smaller than the denominator, and when you're talking about algebraic fractions, that means where the numerator is a smaller denominator, a smaller degree than the denominator, and that's actually what I'm trying to force this fraction to do, so that I can see it in that more standard hyperbola format. I'll show you what I mean. 3x plus 2 over 5 minus x. That is a proper fraction. So what we find here is that so proper fraction is quite a useful thing, and similarly common denominator to put that fraction back together. So fraction tools both in the number and algebra menus. So it's negative 17 on x minus 5 minus 3. And so here we can see right by 5 there's our asymptote at x equals 5, and down by 3. So that horizontal asymptote is going to be at y equals negative 3. So it's going to be option E. Question 6. Part of the graph of f dash of x is shown below. So this is the derivative graph we're seeing, describing the gradient. The corresponding part of the graph of y equals f of x is best represented by. Okay, so I'm going to sort of look at some key points here. So I can see here that the derivative is equal to 0 at those 2 points. So that means that my original function has to have stationary points at those 2 points. Okay, so that lets me rule out A. B might be an option. Okay, again, I've got stationary points at 2 values that are sort of to the left of the x-axis, so that could be an option. C we can definitely rule out. D we can definitely rule out. And E we can definitely rule out. So actually just looking at the stationary points, it takes me to B. If we have a little just check, so we can see here the derivative is positive, so that means positive gradient. So we see that happening here. In between those two stationary points, we see the derivative is negative, so it's negative gradient, so that fits here. After the stationary point, after that second stationary point, we have positive gradient all the time. So we have positive gradient everywhere here, and we can see we've got sort of a bit of bend happening here as the positive gradient gets bigger and then gets smaller. It's still positive, but it's means it's going to be less steep. So it's steeper initially, less steep for a bit, and then steeper again after that. So that certainly fits what we've got. So option B. But yeah, pick some key features, start with those. So the stationary points are what you're going to want to look for, and then see if you need anything else to differentiate. So B for question 6. If f of x is e to the power of g of x squared, so we've got a triple composite there. So we've got an x squared function inside of g of x, an unknown function, inside of an exponential function. And so we want the derivative. So we're not going to be able to just put this in our CAS because g is not a constant, it's a function. If we typed that in our CAS, it would just treat that as if g was a number. So we're going to need to understand what we're doing. And so again, this is where the exam is always going to force you to do this. It's not just going to give you a straight punch the function into your calculator and get it to give you the derivative. Okay, so compositing. So I don't tend to muck around with the chain rule, but you could let u equal x squared and let v equal e to the power of gx and do the first chain rule, and then you could go again. I'm going to see if I can do this all at once. So I'm going to think about covering up my inside function, which in this case is going to be covering up all of that. So initially I have e to the power of something. So the derivative of e to the power of something is still that e to the power of something. Okay, so that means I'm going to get derivative is literally going to be just that whole thing. Right, then we multiply by the derivative of the inside. So this is the inside. So now I'm differentiating g of x squared, and that's going to require a chain rule. So I cover up the inside function, the x squared, and I've got g of something. Derivative of g of something is g dash of that something. And then I need to multiply by the derivative of the inside, which is going to be derivative of x squared, which is 2x. All right, so let's see what we've got, and do we match what we've got happening out here? So it's all written in a slightly different order, but essentially I've got 2x times g dash at x squared times e to the g of x squared. So g dash at x squared, so there's the 2x, there's the g dash at x squared. No, that bit's wrong. The 2x, the g dash at, no, that bit's wrong. The 2x, the g dash at x squared, and that one. So option C. Okay, items are packed in boxes of 25 and the mean number of defective items per box is 1.4. Assuming that the probability of an item being defective is binomially distributed, the probability that a box contains more than 3 defective items correct to 3 decimal places is. Okay, so in 2020 we did have normal distribution and binomial distribution and general sort of year 11 level probability, conditional probability and things like that, but we didn't have general discrete probability distributions, and we didn't have general continuous probability distributions, and we didn't have any of the stats, so no p-hat, no anything like that. Okay, so let's see, we've got items packed in box of 25, mean number of defective items per box is 1.4. Assuming the probability of an item being defective is binomially distributed, okay, so let's have x is the number of defective items, x is binomially distributed, n is going to be 25, we're packing them in 25s, and we don't know p. Okay, so we're going to need to find p first of all, but we do know about the expected value of x. And for a binomial distribution, expected value of x is n times p. So we know expected value of x is 1.4, we know n is 25, p we don't know, so that means p is going to be 1.4 divided by 25, which is 0.056, which you'll see that's a distractor because, don't read the question properly, get an answer, go, oh, great, I'm done. But that's not what the question asks us for. So the question asks us to find the probability that a box contains more than 3 defective items. So now that we know P, we want to work out the probability that the number of defective items is more than 3. So for a discrete distribution, that means 4 or more. Okay, so for our lower bound in our binomial distribution, we're going to use 4. And so we're going to have menu 55B for binomial CDF. Number of trials is 25. Probability of success is 0.056. Lower bound is going to be 4, and upper bound therefore is 25. And so to 3 decimal places, that is 0.048, which is option B. Okay, question 9. If the integral of f of x from 4 to 8 is equal to 5, then the integral of f of 2 times x plus 2 dx is equal to... Okay, so here you're not going to be able to expand out that function because we don't know what f of x is. So you have to rely on your understanding of the transformations that are happening here. Okay, so to get from y equals f of x to y equals f of 2 times x plus 2, there are 2 transformations that are happening there. There's a dilation by a factor of 1/2 from the y-axis, and there is a translation to the left by 2. Now we could go through the x dash y dash process to get to that point, but hopefully you're reaching a point where a couple of simple transformations you're able to identify from the function. Otherwise this question is going to take you a lot longer. Okay, so now what we need to think about is, it's going to get a bit messy and not be a very exact science here, but let's imagine that this is y equals f of x. Okay, and so what we're told is that from 4 to 8, when we integrate that function from 4 to 8, that area there is 5. Okay, now I don't know if it's above the x-axis, I don't know, it doesn't matter, but let's just give ourselves some sort of visual representation of what's happening here. That's essentially the fact we've been given. That's this information here. Okay, so now let's think about, if you now take f of x and dilate it by 1/2 from the y-axis, okay, so let's imagine, I'm not going to get this very right, but let's just imagine we sort of dilate it by 1/2 from the y-axis, so that's f of 2x, okay, and so then if we'd also dilate in this 4, now is at 2, let me get that more accurate than that. That's now 2. Dilating 8 by 1/2 is now at 4. Okay, and if we've squashed, so that blue picture is now that black picture squashed in by a factor of 1/2. So that means we do know what this area is. This area here is 1/2 of 5, or 5 on 2. Okay, so now we're going to translate that whole thing to the left by 2, which means this is going to come back here, this is going to come here, this is going to come sort of here. Right, so we're essentially going to have this happening now. So that's the dilation and the translation, okay? And if we translate this to left by 2 and this to left by 2, we're now here, okay? Integrating from 0 to 2. And if all we did was translate it, we didn't change the area, that orange area is still going to be 5 on 2, okay? So the dilation in by 1/2 essentially told us, the first thing that we learnt was that the integral from 2 to 4 of f of 2x is equal to 5 on 2, and then translating all that to the left takes us to the orange bit, which tells us that the integral from 0 to 2 of f of 2 times x plus 2 is still going to be the same area, because the translation doesn't change the size of that area, it's just moving it somewhere else. So that's just changing where the limits of integration are. Okay, and so that matches what we want here, and so it is going to be option E, 5 on 2. Okay, given that log 2 of n plus 1 is equal to x, the values of n for which x is a positive integer are. Okay, so my instinct is to rearrange this function, because obviously n equals is the format of all of them. We're finding the values of n, so we want to make n the subject. But I'm wondering if it might be easier to think through the positive integer thing from the format we're currently in. Anyway, let's rearrange it and see where we end up. So we're going to have, we rearrange that from a log to an exponential, it's going to give us 2 to the power of x equals n plus 1. And so we get n equals 2 to the power of x minus 1. Okay, so my instinct says that it's probably just b, because that's the only one that gives us the same thing. So the values of n for which x is a positive integer. Okay, so if this thing up here can only be a positive integer, so it can't be 0, okay. So all they've done is they've just replaced the x's with k's, where k is a positive integer, okay. So if we let x equal k, where k is an element of z plus, okay, so we're suggesting that this is going to be the answer. And so obviously if k is a positive integer, then 2 to the power of a positive integer is still a positive integer, and subtracting 1 gives us a positive integer. So these n values will all be positive integers, but yeah, I don't actually think we need to do anything more than that other than to solve for n and say that x has to be a positive integer, which is what this bit here is essentially doing. Okay, so yeah, it's just going to be B, question 10. Alright, question 11. The lengths of plastic pipes that are cut by a particular machine are normally distributed random variable x with a mean of 250 millimeters. Z is the standard normal random variable. If the probability of x being less than 259 is 1 minus the probability that z is bigger than 1.5, then the standard deviation for the lengths of plastic pipes in millimeters is. Okay, so I think a diagram never goes astray in a normal distribution. We could do a whole lot of equations and things, but I think things are going to become pretty clear here. So z greater than 1.5, let's think about if this is a z-axis, then that would be 0. Let's also think about what that would all look like on an x-axis, where the mean is 250, so that would be 250. Okay, so we want 1 minus the probability of z greater than 1.5. So greater than 1.5 means 1.5 standard deviations above the mean. Okay, so if that's 1.5 there, that area to the right is z greater than 1.5, which means that this area to the left is 1 minus the probability that z is greater than 1.5. Okay, and so we obviously want to convert that into a standard normal. So what we're saying here is that that is going to be the same as this being 259 in the z distribution. Now you could use a formula here. Okay, so what we actually know is z is your x value minus the mean divided by the standard deviation. So our z value is 259 and the equivalent our z value is 1.5 and our equivalent x value is 259 minus the mean divided by the standard deviation, and so we get that 1.5 is 9 on the standard deviation, and standard deviation is 9 on 1.5, which is 6. But you can also sort of think quite logically about that. What we know looking at this is that 9 is 1.5 standard deviations, so it's just about working out. That means that 6 is going to be 1 standard deviation. So what we're saying here is that this will be 6, and this will be, sorry, not 6, it'll be 256, so the mean plus 6. And this will obviously be 262. And so 259 is between that. So a diagram when you're doing normal distribution. So a standard deviation is going to be 6 millimeters. So C. Question 12. A clock has a minute hand that is 10 centimeters long and a clock face with a radius of 15 centimeters as shown below. Okay, so at 12 noon, both hands of the clock point vertically upwards and the tip of the minute hand is at its maximum distance above the clock face. Well, the tip of both hands will be, we don't know the length of the hour hand though, so it's just about the minute hand. So that means the tip of the clock face at 12 noon, that's going to be 10. This bit here is obviously 15. And so at 12 noon, H would be 10 plus 15, so 25. the height h centimetres of the tip of the minute hand above the base of the clock face t minutes after 12 noon is given by. Okay, so we know obviously the minute hand has a length of 10, and so that means it is going to go from being up here, its maximum height above the base of the clock is going to be that 25, the 15 plus 10, and the minimum is going to be when that's 10 down there, so it's going to be, the minimum will be 5. Okay, so we know min is 5, and so minimum h, I should say. Min h is 5, max h is 25. Okay, so what we essentially know is that the range of h is 5 to 25, which means that the amplitude is going to be 10, and we've gone up, the graph goes up by 15, okay, to get that range. And so straight away we're going to have amplitude of 10 and up by 15. Okay, that's true in all of those. There's our amplitude of 10, and there's our up by 15. Okay, so we haven't learnt anything new here. Now, the period of this function, it's obviously going to take, for one full revolution, it's going to take an hour. It's a minute hand, okay? And so the period is going to be 60 minutes. Okay, I think t is in minutes. Yep, t minutes. Okay, so the period is going to be 60, which means that 2 pi on n is 60. And so n is 2 pi on 60, which is pi on 30. Okay, so we definitely have pi on 30, so we can rule out these two options with a pi on 60. All right, then we know we're measuring time from 12 noon, and we know that at 12 noon we have a maximum. Okay, so what we know is if this is 12 noon, okay, and then we know obviously at 1 p.m., which will be an hour later, we'll have done one full lap of the circle of the clock. So we back up here, the minute hand will be back at the top, which is 25. And let's put 5 down here. Okay, so we sort of know this is going to be our shape here. Okay, so our period is 60 minutes, or 1 hour. And we can see what we have here is a nice cos shape, because we haven't got any translations, so it hasn't gone left or right. So we could obviously think of it as a negative sign if we started from there, but it hasn't gone to the left or right. So there's no horizontal translation, so we're going to need to think about it in that shape that we're seeing there. So that's going to be a positive cos shape. And so therefore here we have a positive and here we have a cos. So it's going to be this option here, which matches the graph. So option E for question 12. Okay, so question 13. All right, I'm recording this in 2024. I've ended up with a bit of a backlog of these exam 2 solutions. They take a long time to record. So in 2024, there is no longer any matrices on the study design, although this was a perfectly accessible question in 2020 and all the way up to 2022. What we would see is this is a question about transformations, and we could still answer this question. We would just be presented with this information in a different format. So the options here might be, in a 2024 paper, a list of transformations, okay? Dilation by a factor of whatever from the x-axis followed by translation, whatever, okay? Or they might be written, I tend to rewrite these, and the Cambridge textbook certainly has kept the matrix sort of questions and just translated, changed the notation. So in this question, what this information here in this matrix format is telling us is the transformed point xy, which is really just what that means, the coordinates of the transformed coordinates of the point, are equal to, let me expand that in my head, so that's going to be half times x minus 4. And y. Okay, and this is saying the transformed point xy is half times x, sorry, I've got a bit of a lag on my pen at the moment, minus 4. And nothing's happened to the y value. And in this one, the transformed point xy is, sorry, not an arrow, it is equal to Got a real lag happening. Let's try that again. Oh, and I've lost my CAS. Hold on, let me sort things out here. Okay, so our transform point xy in this question, in this option, sorry, is half times x minus 2. Still got that lag. And nothing's happened to y. And in this one, transformed point xy is 2 times x plus 2. Not 0, sorry, just y. And in this one, transform point xy is 2x plus 2. Okay, so those are our options. So transformed point xy is just x dash y dash. Okay, image of x, image of y. Okay, so we just want to know, this question is essentially find the transformations and write them in this sort of point form. And obviously we used to have a way of expressing those as matrices, but the algebra and the process of what being asked to do is still the same. So the question is, the transformation that takes us from this graph to this graph is which of these? Okay, so we can go through our long process here, and I'm just going to have to write a bit small here because I've got taken up all the space with all my options. So y equals cos of x is my original function. We're transforming that to y equals cos of 2x plus 4. Now your transformations might be good enough to do this without the dashes, but these are the ones where students commonly make errors, mixing up the order of these, and particularly the y dilations, getting those the wrong way around. So I put the dashes in my image function. I need both functions to be in the same format, and in this case that's going to be something to do with y on the left equals cos of something to do with x on the right, and so we are already in that format. And so we can now see the transformation, the substitutions that were made. So y is just equal to y dash. There's nothing complicated happening there. Oops, sorry. And x was replaced with 2x dash plus 4. Okay, so we know y equals y dash. Okay, and that's consistent with all of the options that we're seeing here, where y dash is just y, nothing happened to y. But we know that x is equal to 2x dash plus 4. And so if we rearrange to make x dash the subject there, we're going to get x minus 4 equals 2x dash. And so we're going to get x dash equals x minus 4 on 2, which we could also write as half times x minus 4, or we could write as half x minus 2. So now let's see which of those we have. Looks like option A. So up here we can see, oops, sorry, just getting a highlighter. So up here there's half, so x dash is half times x minus 4, and so that's the one we're seeing there, where the transformed x coordinate is half times x minus 4. So option A is going to be our answer here. Again, if you're good at your transformations, identifying them from the function, we would have been thinking about this as being cos of 2 times x plus 2, okay? And that's a dilation by a factor of half from the y-axis, followed by a translation to the left by 2. So half from the y-axis would take all your x coordinates and halve them, and then translate it to the left by 2 would get us this one, sorry, which is that version there. So factoring out that half gives us that version there, which matches the option A. All right, question 14. The random variable x is normally distributed. The mean of x is twice the standard deviation of x. If the probability of x being bigger than 0.52 is equal to 0.9, then the standard deviation of x is closest to. Okay, I'm not sure if the CAS will be able to solve this nicely for us, but let's try it. So x is normally distributed. The mean is twice the standard deviation, so mean is 2 standard deviations. That's essentially what we've got. We know the probability of x being bigger than 5.2 is 0.9. Let's just see if the CAS will solve that. So we're going to do a solve. We're going to get a menu 552, so it's a norm CDF. Bigger than 5.2, so lower bound 5.2, upper bound infinity. Mean is 2 times an unknown quantity, 2s. Standard deviation is just s. And we want that thing to equal 0.5. Now, I'm not sure whether the CAS will be able to handle this. Let's try it. I'm going to solve that for s, and usually when standard deviation is the unknown thing, We just need to help it, I'll give it a little nudge along in the solving here by telling it that the standard deviation has to be positive. Beautiful. And we find that the standard deviation is 2.6, except that's not an option. Okay. What have I done? Mean of x is twice the standard deviation of x. I did that the right way around, didn't I? Oh, sorry, it doesn't equal 0.5, it equals 0.9. Okay, so let's fix that. Just misread the question. So that sort of troubleshooting is a really important thing to practice, okay? What do you do when you find an answer and none of the options are options? You just circle something and move on. What are the sorts of things you're going back and looking for in the question? Have I misread something? Have I interpreted something? My first thing, I thought maybe I'd misread the sentence that the mean was twice the standard deviation. I thought perhaps it was the standard deviation was twice the mean and I'd misinterpreted that or something like that. But then just saying that I've simply just made a typo by writing 0.5 when I meant to write 0.9. Okay, so standard deviation 7.238. So option A. Okay, question 15. Part of the graph of a function f where a is greater than 0 is shown below. I remember this question. The average value of the function f over the interval from negative 2a to a is. Okay, so you could sort of muck around trying to work this out sort of as an area problem, but my first instinct, I remember when this came up, was to do that, but I think that is complicated. So for example, if you understand about average value of a function, I'm just going to draw a different color here. Let's assume that that value there is the average value. Now it's probably not it, I've just made up a number. What that would mean in a geometric sense would be that the area above that value but below the function, so these two blue areas here, would be equivalent to the area below that value but above the function. So we would be looking for that blue line, that average value line, to fall somewhere where the blue areas are equivalent to the orange area. My first instinct, given that everything was on a grid and everything straight lines and triangles, was to think that through. But I seem to recall that actually wasn't as obvious a way of going about it as it seemed. So actually it's really just about working out these functions and setting up a way to calculate the average value. So let's think about this part of the equation. So it's obviously a straight line. We can work out gradient, rise over run. Okay, so negative a up to positive a, so that's obviously got a 2a height, and going from 0 across to a, so that's the run is a. It's clearly got positive gradient, so gradient there is going to be 2a on a, so gradient of that line is just 2. And the y-intercept is at negative a. So that part of the line is y equals 2x minus a. Okay, and this part over here, so again, let's calculate gradient. So we've clearly got negative gradient. So this distance there is 2a. This distance here is going to be a plus 2a, so that's going to be 3a. So your gradient is going to be negative, rise over run. So negative 3 on 2. And again, y-intercept is negative a. Okay, so that's that part of the function there. So for the average value of a function over this interval, we're going to be doing average value is going to be 1 on b minus a, so it's a minus minus 2a. And then we're going to have to split this integral, so we're going to have integral from negative 2a up to 0 of this part of the function, plus integral from 0 to a of this part of the function. And that's a little bit ugly and unwieldy, but we'll just pop that in our calculator. So control divide, we're going to have 1 over a minus minus 2a is just 3a. And then we're going to have an integral from negative 2a up to 0. And the function for that bit will be negative 3 on 2x minus a dx, plus another integral from 0 to a of 2x minus a dx. And that gives us a on 3, which is b. So question 15, option B. Okay, sorry, that was an A on 3 there. All right, so question, my screenshot seems to have done something strange. There we go. Question 16. A right-angled triangle OBC is formed using the horizontal axis and the point C with coordinates of m 9 minus m squared. Okay, so the y coordinate is 9 minus m squared because the equation of the line is 9 minus x squared, and when x equals m, y equals 9 minus m squared. So they very much could have not given you that point. They just could have given you the function and the x coordinate, and you have to work that bit out yourself. Sometimes they might have called this, f at m, and described the function as f of x instead. So this is quite a familiar thing to have a rectangle or a triangle or something inscribed under a curve. Okay, so m is somewhere between 0 and 3, and obviously that's because this is 3 here at the x-intercept. If we solve that equal to 0, we're going to get x squared equals 9, and so x equals plus or minus 3. Obviously the minus 3 is over here, but that's outside the domain. Okay, so maximum area of the triangle OBC is, okay, so it's a max-min problem. We want to maximize a quantity, and we're maximizing area. So we need to come up with an equation for the area, and so it's area of a triangle. So this base of the triangle is clearly m, and the height of the triangle is clearly 9 minus m squared. The coordinates of the point give us that. And so the area, in terms of m, is going to be half times the base times the height. Okay, so that's going to be our function. And so we want to maximize that function. So we want to solve the derivative of that equal to 0, or use function max in our CAS. So I might define the function, or just make things easier to work with. A of m. So you'll notice I always use the variables in my CAS that actually match what I'm writing on the paper. A lot of students I find don't like doing that, and they just always use x, and they always use f of x. And then they get themselves in a muddle when they've got multiple functions in the same question, for example. Obviously, in a multiple choice, you won't have that. But if you've got multiple functions in the same question, and then you called the first one f, and now the second one's g, and all of a sudden you've got 4 different functions defined, and none of them actually match what they're called on the paper, and you're having to constantly remember, oh yeah, f of x was that a of m, and g of x is that function over there, and you get yourself in a real muddle really quickly. And it's also really easy to then, if I defined this as f of x and solve this for x, I would write x equals on the paper when it shouldn't be x equals, it should be m equals. Now again, multiple choice doesn't matter, but just a bigger point. Okay, so I've defined my function. I can solve my derivative of that function. Equal to 0 for m. It's obviously a cubic function, so it's got 2 stationary points at negative root 3 and positive root 3. So if we think about this function is half m times 3 minus m times 3 plus m. So it's a negative cubic with intercepts at 0, negative 3 and positive 3. So we've got this happening there. We've just discovered that that's root 3 and that's minus root 3. So obviously maximum area is happening when m equals root 3. So a dash m equal to 0 gave us m equals plus or minus root 3. Max a occurs when m equals positive root 3. You can see that from the graph. We could also have used function max. And so I'm just going to sub that back into my function to find what the actual maximum area is. So a of root 3. And that's going to be 3 root 3. So maximum area is a of root 3, which is 3 root 3. So D. Question 17. Let f of x equal negative log e of x plus 2. A tangent to the graph of f has a vertical axis intercept at 0c. The maximum value of c is. Okay, so we've got a negative log to the left by 2. So again, my instinct is always to draw, to visualize, to see what's happening. Obviously, you could use your CAS to help you sketch it if you don't know what it looks like. So asymptote at negative 2, it's reflected in the x-axis log, so it's going this way. Okay. So a tangent to the graph of f has a vertical axis intercept. So if we draw a tangent, I don't think it's ever going to have a vertical axis intercept. Have I drawn the right graph? Reflected log left by 2. So if I draw a tangent here, for example, let me just draw any old tangent in. Okay, there's the vertical, this is the vertical axis, the y-axis, okay, and so that intercept is, oh, sorry, I thought it was, sorry, my apologies, I misread it. So it just talking about the vertical axis intercept is just the y-intercept. Okay, the tangent has a y-intercept, but obviously there's no y in this problem in the way it's been defined, so I haven't actually defined the vertical axis as being a y-axis, so they can't just say y-intercept. And so that point is at 0c. The maximum value of c is. Okay, so obviously if our tangent was up here, c is going to be much lower down than that. If our tangent was here, c is going to be lower than that as well. So actually, I think the maximum value of c is going to be when the tangent is actually at c. And so therefore, it's just going to be at the y-intercept. So again, visualizing helps you to see it, okay? So the maximum value of c is going to be at that y-intercept of the function. And so we need to work out the y-intercept, which is f at 0, so negative log e of 2. And so it just should be option C for question 17. So it's really important to see what's happening here. You could have set out, tried to solve, setting up an equation and maximizing it, etc., but you can actually visualize what's going on and understand that wherever you move that tangent to, the maximum possible value, the highest possible y-intercept will be when we draw the tangent actually at the y-intercept. And so therefore it's nice and easy once we see what's going on. Okay, question 18. Let A be a positive real number and B is any real number. So again, just flexibility with your notation. Obviously that's just the same as R plus. It could have said that. It doesn't matter as long as we can interpret and understand all those different notations. Consider the function h. Okay, so h has a sort of domain that goes from negative a to a but doesn't include 0. And it's a hyperbola, which is why it can't include 0, why the domain can't include 0. The range of h is, okay, so again, let's visualize. So this is a hyperbola with a bit of a dilation from the x-axis and a translation up by b, or down. B could be a real number, so up or down. All right, so let's just think about what's happening here. I think maybe let's think about the two possible options. Let's imagine when b goes up, first of all. So if b is positive, that is. So if b is positive, we're going to have essentially that. It's a hyperbola, a bit of a dilation. Let's say that that's a and that's minus a. Okay, so note actually that the domain and that dilation factor are actually connected to each other. So they're the same value. So a to negative a. So we're essentially going to have, including those points. Okay, so that would be what would happen if we would go up by b. So let's think about the coordinates of this point. So if we substitute a into here, we're going to have a on a, which is just 1 plus b. So it's just going to be b plus 1 or 1 plus b. So that's a, b plus 1. And this point here is negative a. So if we put negative a into here, we're going to obviously have a divided by negative a. So it's negative 1 plus b. All right, that is b minus 1. Okay, and so if we think about range here, range is going to go everything from negative infinity all the way up to and including that value there, which is b minus 1. And then it's going to have a bit of a gap, and it's going to kick off again here at b plus 1 and go all the way up here. Now that's not going to change if b is a positive or negative number. That graph's just going to shift up and down, but that's going to be the same thing. So our range is going to go from negative infinity up to b minus 1, including b minus 1. And then we're going to have a little jump. We're going to have a union with b plus 1 all the way up to positive infinity. So obviously we can't include the infinities, but we do want to include the b minus 1s and the b plus 1s. So that's going to be D. Shown below is the graph of P, which is the probability function for the number of times X that a 6 is rolled on a fair-sided die in 20 trials. Okay, let Q be the probability function for the number of times W that a 6 is not rolled on a fair-sided die in 20 trials. Okay, so the only thing that would change if it's not rolled, so in this case, X is the number of times that a 6 is rolled, and so X is binomially distributed, it's rolled 20 times, and P is 1/6, okay? And so this peak here will be happening at 1/6 of 20. Well, 1/6 of 20 is 3 point something, so, you know, the peak's sort of somewhere a bit over here. And so what we would see happening is, in not rolled, all that's going to change is that W is binomially distributed, still N is 20, but this time P is 5/6, okay? And so we're going to see that peak happen at 5/6 of 20. So we're essentially going to see the mirror image of this, but it's going to mirror around 10, right? So that point is going to flip over there to here, and that point's going to flip over here to here, and this point, sorry, you can't see where I'm pointing, this point here is going to flip over to here, and this one's going to come to here, and this one's going to come to here, and we're essentially going to get the mirror image of that. So we don't have a nice transformation to reflect in the line x equals 10, so we need to think through what that's going to look like. So there's a couple of different ways we could think through those transformations. We're either going to translate that original shape. So you can just think about it as a curve. It's not a curve, it's a series of points, but it doesn't matter. For the purposes of this, we can treat it as a curve. We essentially want to go from, let me change the color. Sorry, that's not going to be very nice. It's going to actually hit that same point there. It shouldn't go under there either, but you know what I mean. So obviously the probabilities are getting smaller and smaller and smaller. So we want to be able to essentially reflect in y equals 10. So as I said, we can only reflect in the axes. So what I want to think about is taking this black shape, if I translated it all the way back here by 20, so that all of those 20 points are now sitting to the left of the y-axis, and then I reflected it in y, that's going to get me from the black graph to the blue graph, okay? So we need to translate left 2, then reflect in the y-axis. Now, you might have thought through those transformations slightly differently. You would be able to do a reflection and then a translation. You'd reflect in the y-axis and then translate, sorry, not left 2, left 20. And then you translate it to the right by 20. But either way, we're going to get to the same place. So if we take a point xy and we first translate it to the left by 20, that's what happens to it. And then we reflect it in the y-axis. We take this whole x coordinate and multiply it by -1. So we get negative x minus 20. Okay, so we know x dash is negative x minus 20, and we know y dash is just y. And so rearranging this, x is going to be negative x dash plus 20, and y is just y dash. And so if we're going from y equals p of x, and we're doing these transformations, we're going to get y dash equals p of negative x dash plus 20. Okay, and so that's the same as p of 20 minus x dash. Okay, and this is the rule now. This is now q of w. Okay, so we are going to take this one here, option A. Is going to be the same function, different variables. We're changing the x from x to w now that we've done these transformations, but that's going to give us the right graph shape. Okay, so question 19 is option A. All right, and then question 20. Let f of x equal cos A of x. Domain is R. A can be any positive real number except for 0. Obviously, the function wouldn't be defined if A was 0. So it can be negative. Sorry, I said positive real number. It could be any real number, so it could be negative. So if a was a negative value, that would reflect our cos graph in the y-axis, but actually given the shape of a cos graph, that doesn't actually change the shape of the graph at all. So it's really just about changing the period. F of x is equal to f of x plus h for all h is an element of z. Okay, that's fine. So there's some kind of horizontal translation that we could apply to f of x and still end up with f of x. And that happens with trig functions. If you think about what we have here, what we've got here is some sort of cos graph, sorry, just with a period change. The period is 2 pi on a. Okay. And so therefore we know that if we were to translate this graph by a whole period, we still get the same graph. So if we were to translate left or right by 2 pi on a, then we would get the cos graph again. Alright, so we want to let g be a log function. Oh, sorry, no, it's log of this cos function with an unknown domain. It needs to be a function where the range of g is -1 to 0. A possible interval for d is. Okay, so there's quite a lot for us to think through here. So d is the domain of a composite function. Okay, the domain of the composite function is just the domain of the original function. But we need to work out, and obviously it's not just r, because we need to work out, well, how do we might need to adjust this domain in order to make sure that when we do this composition, this thing here happens. Okay, all right, so let me think this through again. So what do we know? We want the range of g to be from -1 to 0. All right, so let's just think about log 2 of something first of all. Okay, so if the graph of log 2 of something, log 2 of x, is just going to be that. Okay, and so it has a range of r. Okay, now we want the range of log 2 of something to just go from -1 to 0. Okay, so we now are interested in -1 to 0. Okay, so what I'm interested in is thinking about what that means for the domain. Okay, so this is definitely 1, 0. What I want to know is that value there. Okay, so if log 2 of x equals -1, that's x equals 2 to the power of -1, so that's half. Okay, so what that means is for a log function or a log base 2 function to have a range from -1 to 0, it means that the thing inside it has to be between half and 1. Okay, so what we now know is from this is we need, can it include half? Yes. We need f of x, the thing inside the log, to be somewhere between half and 1 inclusive. And then that will give us this range that we want here. Okay, so now let's go back to our f of x function. So f of x is a cos function. With just an amplitude change. Okay, so that means it actually goes from -1 to 1. Okay, so obviously we don't want that much of it. So we only want it to be between 1.5. Okay, so we actually just need to work out which of these 5 domains here gives us a part of this graph that's in this little window here from half up to 1. Okay, do we need to know what A is doing? Yes, I think we're going to need to think about A first because none of these domains will actually apply given that at the moment we only know that that's going to be 2 pi on A. So I think we need to use this property first of all. Okay, so let's go back up to there and think about, so we started thinking about that before, I had a little graph drawn and then I've stopped. Okay, so what we know is that f of x is equal to f of x plus h. So let me just see what happens if we solve that. So let's just try something. Let's define our function f of x as being, sorry, got distracted, being cos of a times x. A is already defined. Let me clear A to Z. Menu 1.4, clear A to Z. It's also going to clear my f of x definition. Let's do that, just do that again. So now the A is not bold. I could have used a different letter, but like I said, you get yourself muddled up quickly if you change them around, you lose track of what's what. Okay, I'm just going to see what happens if I solve f of x equals f of x plus h for A. Okay, no, I think we need to think logically about that. Okay, so like we said, there's our cos graph. It currently has a period of 2 pi on A. So the only way this statement is true is if we are translating by a full period. So if h is plus or minus 2 pi on A, okay, so the key here though is that this statement is true for all h, for every integer h. So if we don't if h is 0, we don't translate it anywhere, that's true. If h is 1, we also need that to be true. So we need, for example, f of x to be equal to f of x plus 1. Let me see if I just do, let's see what happens if I do this. But also going to be true if, let me see if we can, I don't think it'll like this either. Just thinking because we've got two unknowns in that. What if we told it that f of x is the same as f of x plus 1, and also that f of x is the same as f of x plus 2. Obviously it's true for every single integer. No, okay. I think we need to still think graphically about it. Alright, so let's just have a think about this statement. So I'm just trying to get myself some more room to write. So f of x equals f of x plus h. F of x is cos of ax. And f of x plus h is cos of a times x plus h. Okay, so they both have the same period. The only difference is that translation to the right by h. So when it's written okay, so what I think we need to think about here is, let's just think about that cos of ax. So let's imagine a is 1, okay, to start with. So if a is 1, then this would be my cos graph, okay, that would be 2 pi, and this would be this, no matter, we could translate it to the right by 2 pi okay, I think I just realized what the problem is, because I'm confused about sort of the pi's and the translation. So obviously if a was 1, your period is 2 pi, and you would then have to be able to translate the graph to the right by 2 pi or 4 pi or 6 pi or a multiple of 2 pi, right? Except, so an integer multiple of 2 pi would work. Except the problem is that we know this has to work for not an integer multiple of 2 pi, it has to work for all the integers. So we should be able to translate this graph to the right by 1 or 2 or 3 or 4, or left by 1 or 2 or 3 or 4, and still have the same graph. So the only way that that actually works is if the period is 1, okay? And so we're going to need, for this statement to be true, sorry, I've got things drawn everywhere here now. So for it to be true, for if we translate it left or right by any integer value and still have the same function, that only is going to happen if the period is if the period is 1. Okay, and so that means that 2 pi on a has to be 1, and so therefore a has to be 2 pi. So the only way that this statement works is if a is 2 pi, and that is that we have a cos graph with a period of 1, and therefore if we translate it to the left or right by any integer, by 1 or 10 or 7 or 6 or 754, it'll still be the same graph because the period is 1. Okay, so that's actually the hardest thinking part of this. Now we've done the work we need down here. So now we know that this is not 2 pi on a here. Our period is going to be 1. So this is going to be 1 and 2 and minus 1. Okay. So this is just now the graph of y equals cos of 2 pi x. Okay, and so now we need to work out which of these domains gives us a range that's only in this blue region from half to 1. So remember, we're looking for the domain to be such that the graph only sits in this section here. In fact, it has to reach fully, the range needs to be from -1 to 0, so it has to span that full highlighted range I've just drawn in there. Okay, so let's see if we can rule out some options here before we go looking at the CAS. So obviously, if our period is 1, that makes this a half, that makes this a quarter, and that makes this 3/4. So if the domain was 1/4 to 5/12, 5/12 is a bit less than a half. So 1/4 to 5/12 would be from here to here. Okay, so that's definitely not going to be right. 1 to 7/6. So 1 is going to be here. So let's give us some more options. This would be 5/4. This will be 3 on 2. This will be 7/4, etc. Okay, so 7/6 is just a bit more than 1, so just 1/6. So I think that's going to be within the region, but I'm not sure that it's going to come all the way down to here. So we might need to think about that one. 5/3 to 2. 5/3 is, just trying to work out roughly where it is, say relative. So it's 1 2/3. Is 5/3 bigger than or less than 7/4? So 5/3 into 12ths is going to be 20/12. 7/4 is 21/12. Okay, so 5/3 is going to be a bit before here. So that means we're going to come down to here. So that one, option C, is going to span out of that blue range. So we can definitely get rid of that. -1/3 to 0. So -1/3 would be past -1/4. So again, remembering, sorry, I know this diagram's gotten crazy. This is going to be -1/4 here. This is going to be -1/2 here. So -1/3, it's more than a quarter, but a third is more than a quarter, but less than a half. So -1/3 is going to be sort of somewhere here. So that would be looking at all of that bit of graph there. So definitely not that one. -1/12. 1/12 is definitely smaller than negative a quarter, so it could be up in this range here, negative a twelfth. But then we're going to go all the way to a quarter, which would take it all the way around to there, so that would definitely come out of there. So I think it's probably this one, but let's maybe just have a quick look at that. So let's maybe sketch the graph of cos. Let's sketch the graph of, let's do the whole thing, and this is perhaps how we could have come straight away to check it out here. So 2 times pi times x. Alright, let's just, we don't need to go any further than 2, so let's do some adjusting here. Let's make that minus 1.5 and 1.5, and let's make that, there's going to be too much going on here, go through the menus. Menu for 1, let's go just from negative 1 to 2. Okay. So now if we drew that same graph, so I'm going to draw f1 of x again. Oops, sorry, f1 of x. But just for, let's just have a look for interest's sake at that first domain. So given that, we're going to go from a quarter being less than or equal to x being less than or equal to 5/12. Okay, so that's down there, which is not what we want. So let's also draw in the line y equals a half. Okay, so remember we need to be above that line. So this f2 of x is not what we want, so it's definitely not option A. Now we queried option B, so let's edit this domain here to go from 1 to 7/6. So 7/6. Okay, I think that looks good. Yeah, so that's going to give us the domain that we want. Sorry, the range that we want. The range will be from half to 1. So again, let's just check. So we could do f1 of what was it? 1 is definitely 1, and f1 of 7/6 is definitely a half. Okay, so that definitely does give us the range that we want. And so option B is going to be our answer to question 20. So a pretty curly one at question 20. And this is where working through an exam, you need to be strategic. You know, for many of you, this might have been worth, having your guests a bit sooner and moving on and coming back if you had time later on, rather than sitting here for quite as long as I have. Okay, so let's move on to section B. Okay, so as we saw from the cover sheet, section B comprises 5 extended response questions. Looks like this first one is worth 11 marks, so 1.5 times 11 is going to be 16.5 minutes. Should take me this. So you want to work out that kind of pacing during your reading time. All right, just going to clear my CAS. Just going to do a clear A to Z after having done all the multiple choice and a menu 1.5. Let's go over my graphing screen, delete, delete, delete. We'll get rid of everything there. And menu for 5, zoom standard will take us back there. Okay, so here we have a function. It is a quartic function. We have a picture of it. We have an equation for it. Looking at the equation, it makes perfect sense to us that we have x-intercepts at +2 and -2 with bounces or touches at each of those x-intercepts. Okay, so we want to show that A is equal to a quarter, so that's going to be to do with the y-intercept. If we were to substitute either of these x-intercepts into this function, all we would learn is that 0 equals 0, because the x-intercepts are what has already enabled us to come up with these values in the brackets. So we need a third bit of information to come up with that dilation factor out the front. Okay, so we're going to need to do f of 0 equals 4. Just move that over just for space. Okay, so f of 0 is going to mean a times 0 plus 2 squared times 0 minus 2 squared has to equal 4. So it's going to be a times 4 equals 4. So 16a equals 4. And so a is 4 on 16, which is a quarter. So don't forget in a show that question, you want to be really explicit about those steps. So if this wasn't a show that, I might have jumped straight here and done the substitution and simplification of that in my head, but it's a show that. So I'm showing that I substitute zeros in place of the x's in the function. So everywhere there's an x up here, I've replaced it with a 0. I've started with that. That is just subbing 0 into the function, making it equal to 4. And then one step at a time, I gradually work down to end up at a is equal to a quarter. Okay, so now that we know a is a quarter, let's maybe define that function. I'm sure we're going to need it. So we're going to define f of x equals a quarter times x plus 2 squared times x minus 2 squared. Okay, express f of x equals a quarter times, okay, so that's the function, in this particular form where b and c are integers. Okay, so it's not asking us to show anything here. It's just a 1-mark question with an answer. So it's really just about getting it in that form. So that's just going to be a straight expand. So I'm just going to do menu 3, which is expand. I'm going to expand f of x, and that's going to give me that. And so f of x equals 1 quarter times x plus 2 squared times x minus 2 squared. We've just established that that is the same as 1 quarter times x to the power of 4 minus 2x squared plus 4. So the question doesn't ask me to find b and c. This isn't about stating that b equals -2 and c equals +4. It's just about writing the answer in that format, which is just a simple expansion. Okay, part of the graph of the derivative function is shown below. Okay, so that makes sense. We know that there are turning points at -2 and 2 and also at 0. So our derivative function has x-intercepts at those 3 values. So the derivative is 0 at those 3 values. So everything looks right here. Write the rule for f dash of x in terms of x. Okay, well I could just differentiate my function up here to get the derivative. Let's see what form it gives it to me in. Okay. So f dash x is going to be x times x minus 2 times x plus 2, which also fits with that diagram. That's a cubic with intercepts at 0, 2 and -2 is a positive cubic, so that matches what I'm seeing in the picture perfectly. You might also have, if you expanded out, if you differentiated the expanded version here, you might instead have had, what's that going to give us, x cubed, just write that more clearly, x cubed minus 4x. Either format, it would be correct there, it doesn't specify the form. Find the minimum value of the graph of f dash of x on the interval from 0 to 2. Okay, so over this bit of domain here from 0 to 2, okay, we want to know what the minimum value of f dash of x is, so that's just finding the minimum value here. Okay, so we're going to want to know where the turning point of the derivative is. So we're going to want to solve, we're going to want to differentiate the derivative and solve that, and that's going to give me these x values here. Okay, so I'm going to solve the derivative with respect to x of the derivative equal to 0 for x. Okay, so that tells me that those turning points of the derivative function happen when x is plus or minus 2 root 3 on 3. We're only interested in the one in this domain, so we're only interested in the positive one. And so we want the value of the derivative. So it's the minimum value of the derivative function. We're not subbing it back into the original. So we're substituting the positive one of those into the derivative. So I'm going to take that, given that, and I might just copy that because that's going to be quicker, but I want to get rid of the one that I don't want. Okay, so we've substituted that into the derivative, and we found the minimum value of the function there is going to be minus 16 root 3 on 9. So min value of f dash is minus 16 root 3 on 9. over this domain. Obviously, we can see down here there are lower values of the derivative, but if we're just focused on the domain from 0 to 2, that's the minimum value of the derivative. Okay, so now let h be this function here. Okay, so if we notice here, that's f of x there, okay? So what we essentially have here is negative f of x plus 2. So we've got reflection in the x-axis and then up by 2 to get from f to h. So that's what we've seen here. We've reflected f in the x-axis and then shifted it up by 2 to get to h. Okay, write a sequence of 2 transformations that map the graph of f onto the graph of h. Okay, we just did that before I even read the question. So I'm going to make sure I use the correct language. I'm going to be less shorthand than I was in my little dot points up there. So we have a reflection in the x-axis. So we don't reflect on or over an axis. If you look at your reflection in a mirror, it is a reflection in a mirror, not on the mirror or over the mirror. So we're reflecting in the x-axis. And then we need to use the word translation, not shift or move or anything like that. Translation up by 2 units. And you can say up, down, left, and right. Some people, go into a lot of detail saying in the positive direction of the y-axis, which you can, but you don't need to. Okay, so just 1 mark for both those things. Okay, so maybe while I'm over here in my CAS, let's define that h of x. Let me define h of x as being negative f of x plus 2. It's quicker doing it that way than having to rewrite it all out. Okay, state the values of x for which the graphs of f and h intersect. Okay, so we want to solve f of x equals h of x. So let's do that with our CAS. I've got them both defined now. So I'm going to solve f of x equals h of x. Sorry, h of x for x. Alright, and we can see from the graph that there's 4, and we found 4 here. Okay, and that happens when x equals negative root 6, negative root 2, positive root 2, and positive root 6. Write down a definite integral that will give the total area of the shaded regions in the graph above. Okay, now interestingly, it does say a definite integral, which to me suggests 1 definite integral. I would have done it with 1 anyway and just doubled it because we clearly have 2 symmetric shapes here, but I'm interested in whether an expression that involved 2 definite integrals would have been accepted, given that it specifies to write down a definite integral. Okay, I've just had a quick look at the examiner's report, and it did suggest that it was possible to write down an expression for the area that involved multiple definite integrals, but I think therefore that's possibly a slightly misleading phrasing of the sentence. Okay, so the total shaded area, okay, so the area is going to be 2 lots of the integral from, I'll do the one with the positive limits, so that's therefore going to be from positive root 2 to positive root 6. So I'm looking at this one over here. And in that area there, the top function is h and the bottom function is f. So this is going to be h of x minus f of x. You don't need to write out those whole functions again. They are clearly defined in this question. We all understand what f of x and h of x refer to. So that's a definite integral that will give the total shaded area of the regions in the graph. So the integral gives the yellow area that I've got highlighted up there, and then doubling that will give the total shaded regions. It doesn't tell me to evaluate that integral. I'm sure it will ask me to do that in this next question. So making sure you're answering the question. Just write down the integral or integrals. Part 3, find the total area of the shaded regions. Okay, so let's do that. 2 times shift plus square root of 2 to the square root of 6 h of x minus f of x dx. And it's correct to 2 decimal places, so control enter to get me a approximate version. Okay, and so that area is going to be approximately 2 decimal places, 2.72 square units. Okay, let D be the vertical distance between the graphs of f and h. Find all values of x for which D is at most 2 units. Give your answers correct to 2 decimal places. Okay, so the vertical distance is just going to be the difference between the two functions. So h of x minus f of x, or f of x minus h of x. But we need to be a bit careful about, obviously, if you're going to define the distance as being, I'm going to go f minus h, let's say. So let's say that the distance is f of x minus h of x. Then that will give me a positive value as long as f is above h. So it's going to give me a positive value between negative root 2 and positive root 2, and when x is bigger than root 6. But in these little intervals here, between root 2 and root 6 and negative root 2 and negative root 6, it'll give me a negative value. So we need to be a little bit careful about that. So you can avoid that by just defining the distance function as the absolute value of this, and this is where them taking the absolute value function out of the course has actually made things harder, because some of you know it and will use it, and it's actually easier. But I'm going to avoid using it because it's not actually in the course anymore. So we just need to be a bit careful, because actually what this would mean, if we want the distance to be at most 2 units, that means that we want the distance to be less than or equal to 2, but actually it could also be bigger than or equal to negative 2, because if D is negative 2, that just means that H is above F, but the distance between them is still going to be 2. So actually what I need is this. Alright, so let me first of all, over here in my CAS, I'm going to define my D of x function. And it is going to be f of x minus h of x. And then I'm going to solve. Negative 2 is less than or equal to d of x, which is less than or equal to 2. And solve that for x. Good, and I want 2 decimal places, so let's hit Control Enter on that. Okay, so that is going to happen. So negative 2.61 is less than or equal to x is less than or equal to negative. They often talk in examiners' reports about transcription errors. That would be an example of a transcription error where I just lost the negative as I was concentrating on decimal places and all those other things. Okay, so negative 2.61 to negative 1.08, or 1.08, I imagine it's positive 2.61 on the other side of that. Yep. Oops. Less than or equal to x less than or equal to 2.61. Find all values of x for which D is at most 2 units. Okay, so that would be our solution. Okay, so question 2. An area of parkland has a river running through it as shown below. The river is shown shaded. Okay, sorry, the river, I read it as river shown is shaded, but it's the same thing. The north bank of the river is modelled by the function blah, 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 blah. The south bank of the river is modelled by the function blah, blah, blah. Okay. The horizontal axis points east and the vertical axis points north. All distances are measured in metres. Okay, a swimmer always starts at point P, which has coordinates of 50, 30. Assume that no movement of water in the river affects the motional path of the swimmer, which is always a straight line. The swimmer swims north from point P. Okay, so the swimmer's going to swim from here north. Find the distance in meters that the swimmer needs to swim to get to the north bank of the river. Okay, this is just going to be the difference between these two, difference between these two functions. So these two functions are exactly the same in terms of amplitude and period. It's just one is up by 40 and the other one's up by 30. So that means the distance between them, the vertical distance between them, is just 10 metres. It's just a 1 mark question, so we don't need to do anything other than that. It's also going to be, that distance there, that distance there is 10, and so the vertical distance the whole way along the river is always going to be 10. or the northerly distance, I should say, north-south distance. The swimmer swims east from point P. Find the distance in meters that the swimmer needs to swim to get to the north bank of the river. Okay, so this time the swimmer is going to swim east, which is this way. So we need to work out that distance there. Okay, so remember, this value here is y equals 30, so we want to make f1 of x equal to 30. Okay, let's define these two functions. Let's just do some clearing here. If you're working in document mode, I'd start a new document. Okay, so I'm going to define some functions. I'm going to define f1 of x as being 20 times cos, pi times x on 100 plus 40. Alright, and then I'm just going to edit that to define the other one. Let's make that 30. Let's make this f2 of x. Okay, great. Okay, so what I need to answer this next question is I need to find that point there, okay, and that is where f1 of x is equal to 30. So I'm going to be solving f1 of x equals 30. And obviously that will give me infinitely many solutions because I would get this one over here and the next one, etc. So I can see that I want the solution between 50 and 100, so I'm going to restrict that domain in the CAS. So let's solve f1 of x equals 30 for x, but we only want the solution that we can see between 50 and 100. Okay, so that happens when x equals 200 on 3. So that's not the distance the swimmer swims. So the distance swum is going to be the difference between 50 and that. Okay, so the distance swum is going to be 200 on 3 minus 50, which is going to be 50 on 3 meters. Doesn't tell me to give a rounded decimal answer, so I'm going to leave that nice and exactly. Okay, on another occasion, the swimmer swims the minimum distance from point P to the north bank of the river. Find this minimum distance. Give your answer in meters correct to one decimal place. Okay, so the minimum distance is going to be the perpendicular distance. So the minimum distance is going to be what happens if I swim at a right angle from this bank. Okay, and that's going to give me my minimum. So there's a number of different ways that I can do this, but what I might actually do is find the equation of this normal. Okay, so this line is the normal at the point P. So I'm going to find the normal to f2 of x, which is the south bank, at P. So menu for A for normal. It's a normal to f2 of x. Oops, sorry, I keep doing that today. At x equals 50, which is the x coordinate of P. Okay, and that's that. It's a bit ugly, but let's write it down. So it's y equals 5 on pi x, and then plus that ugly fraction. I'll write that as 10 on pi times 3 pi minus 25. And then I want to know where that normal intersects with f1 of x. So I want to solve that. Equal to f1 of x, which is the northern bank. and it's all decimals, so that's good. So x is approximately 54.5. Okay, so that is this point here. Now I know that point has an x coordinate of 54.5, and we'll need to find the y coordinate, and then we'll find the distance between these 2 points. Okay, oh sorry, I went too far. Okay, and so that's going to mean running out of space here. I might put this over here. Sorry, just trying to organise my... grabbed something I didn't mean to. Okay, so let's do f1 of that. f1 of x, given that x is that. Okay, so that's 37.17 or 18, sorry. Okay, so the coordinates of that point on the other, of the closest point on the other side of the river are this. So this is the closest point. Sorry. Closest point. Okay, so the shortest distance is going to be the distance between those 2 points. So that is the square root of 54.5 minus 50 squared plus 37.18 minus 30 squared. Okay, so square root of, oops, sorry, struggling with the CAS today, of that value minus 50 squared plus that value minus 30 squared. So that's just the distance between 2 points formula, which is really just Pythagoras. And we want this distance correct to 1 decimal place. So that is going to be 8.5 meters is the shortest distance, which is definitely shorter. The vertical distance, remember, was 10 meters if we swam straight north. If we swam straight east, it's this 50 on 3, which is a lot more. And so 8.5 meters is the shortest distance if I swim perpendicular from the bank. Okay, calculate the surface area of the section of river shown on the graph on page 16 in square meters. Okay, so we just want that area, so it's just going to be the integral of f1 minus f2 from 0 to 200. Integral from 0 to 200 of the top function, which is f1 of x, minus the bottom function, which is f2 of x. Okay, let's do that. Shift plus, integral from 0 to 200, sorry, lost the 0, of top function minus bottom function. And that is 2,000 square meters. A horizontal line is drawn through point P. The section of the river that is south of the line is declared a no swimming zone. Find the area of the no swimming zone correct to the nearest square meter. Okay, we're going to need to be a bit careful here, I think. Alright, let's draw this. So a horizontal line is drawn from point P. So we're going to draw a horizontal line. Okay, so all of this is the no swimming zone. Okay, so actually we need to be a bit careful here. So we're going to need to split this into some different regions. We're going to need to know that bit there. We're going to need to know that point there. And I'm going to assume because of symmetry that that's 150, but let's calculate. So we actually already worked out that value there. That was 200 on 3. So let's maybe go back up here where we got that. So let's solve that for everything from 50 to 150. Oops. I think it should actually also include 50 and 150. Let's make that 40 and 160. It's interesting that it doesn't actually... Oh, sorry. No, that's right. It's because I'm solving f1 of x. So this point here is 400 on 3. And then we would need to solve f2 of x. Sorry, let's go back. So we'd need to solve the other function to find those other 2 points, which should be 50 and 150. Yeah. Okay, so I'm going to integrate from 50 to 200 on 3, and the top function there is going to be y equals 30. So it's going to be 30 minus f2. From 200 on 3 to 400 on 3, it's going to be f1 minus f2. And then from 400 on 3 to 150, it's going to be 30 minus f2 again. Okay, so the no swimming area is going to be the integral from 50 to 200 on 3 of 30 minus f2 of x plus the integral from 200 on 3 to 400 on 3 of f1 of x minus f2 of x plus the integral from 400 on 3 to 150 of 30 minus f2 of x. Don't forget all your dx's. Okay, and we want the area to the nearest square metre. Okay, so 50 to 200 on 3, 30 minus f2 of x. Okay, that's that bit. I should have just done it all at once. That's okay though. It's going to be 200 on 3 to 400 on 3 of f1 of x, oops, minus f2 of x dx, and then it's going to be 400 on 3 to 150 of 30 minus f2 of x. Okay, so we need to add those three things up. So we're going to have that amount plus that amount plus that amount. Control Enter, and that is going to be 837 meters squared to the nearest square meter. Okay, so part F. Scientists observe that the north bank of the river is changing over time. It is moving further north from its current position. They model its predicted new location using the function width rule. Okay, so it's moving further north, not via translation, but via dilation. So being dilated away from the x-axis. Find the values of k for which the distance north across the river for all parts of the river is strictly less than 20 meters. Okay, so the distance north just means the vertical distance. So if you were at any point to swim straight north, you want that distance to be less than 20 meters. The difference is when you're dilating the function, this point won't dilate as far as this point, right? So dilation is going to do that, which means that distance is going to get a lot bigger and that distance is not going to get quite as big. Okay, so this is going to be k times f1 of x. Okay, and the northern distance between those two functions, so essentially the width of the river, the vertical width of the river, is going to be k times f1 of x minus f2 of x. Okay, so the new distance is going to be k times f1 of x minus f2 of x. And we're going to need that distance to be less than 20 meters. Okay, and we're interested in that. And we want that to be true over our domain, which is 0 to 200. I think. I'll just check. Yeah. Okay, so, and we want to solve that for k. So let's see what happens. So we're going to solve k times I'm not going to be solving that for k though. Let me see what happens. Solve k times f1 of x minus f2 of x has to be strictly less than, so not even less than or equal to, has to be less than 20. And I'm going to solve, yeah, let me try solving that for k, given that x has to be between 0 and 200. Let's try that. Not sure that it's got enough information to solve. No, it hasn't. I have to think about that. Well, I mean, I think I probably don't need to solve a complicated equation. The furthest point is going to be this point up here, which is going to become 60k. And that's still going to be 50. Everywhere else, they're going to be closer together. So I actually just need 60k minus 50 to be less than 20. Which means 60k has to be less than 70. So k has to be less than 70 on 60, which is less than 7 on 6. And obviously also k has to be bigger than or equal to 1. So therefore the values of k, otherwise if k is less than, or less, if k equals 1, nothing's changing. If k is less than 1, the graph would squash down and we're not moving it away from, we're not moving the river further north. So 1 is less than or equal to k, which is less than 7 on 6. Okay, and then we are on to question 3. Okay, so question 3. Sorry. A transport company has detailed records of all its deliveries. The number of minutes a delivery is made before or after its scheduled delivery time can be modelled as a normally distributed random variable, t, with a mean of 0 and a standard deviation of 4 minutes. A graph of the probability distribution of t is shown below. Okay, so if the probability of t being less than or equal to a is 0.6, find a correct to the nearest minute. Okay, so that's just a straight inverse normal question. Menu 553 for inverse normal. Area is 0.6. Remember, it's the cumulative area from the left. So t less than or equal to a is 0.6. So we're essentially saying, a is somewhere here and all that area is 0.6. So that's the way we want it for inverse normal. We want the area coming from this direction. So that's all good. We'll just put 0.6 in as the area. Mean, we can see from the, oh, okay. So only should be variable t. Okay, the mean is 0. Now, I suspect that we're meant to assume that 12 is 3 standard deviations from the mean. And so therefore 1 standard deviation is 4. But that's not an assumption I would expect them to make you make in an exam. Okay, let's see what that gives us. Okay, I'm pretty sure that matches the answer in the solutions. Just let me pause and check. Yes, so the examiner's report confirms standard deviation of 4 minutes. Phew, Okay, it does say. Sorry. Read the question. Sorry, I had a little break and my brain's not in the zone. Okay, so a standard deviation of 4 minutes, mean of 0, so we've put all that in, and so we've got A is 1 minute. Correct to the nearest minute. Find the probability correct to 3 decimal places of a delivery being no later than 3 minutes after its scheduled delivery time, given that it arrives after its scheduled delivery time. Okay, so we want the probability that the time is no later than 3, so time is less than or equal to 3, given that it was late, so given that the time was definitely bigger than 0. Okay, so it's a conditional probability, so we need the intersection of those two things. So that is the probability that it is between 0 and 3 over the probability that t is greater than 0. Now, whilst for a normal and a continuous distribution it wouldn't make any difference in terms of the calculation as to whether these were less thans or less than or equal tos, or greater thans or greater than or equal tos, I think it's important, and look, I can't say what VCAA will do, but I think it's important to accurately interpret the question. So no later than means less than or equal to. It can be 3, but it can't be later than 3. Okay, so I think that matters. Similarly, given that it arrives after its scheduled delivery time, well, after means that it is more than, greater than. Okay, so I can't predict what a VCAA assessor would do, but to me, I think part of the method is an accurate interpretation of the wording of the sentence. Okay, let's calculate these probabilities. So we're going to have menu 552, lower bound is 0, upper bound is 3, mean is 0, standard deviation is 4. Okay, so that's going to be 0.2734 over t greater than 0 is going to be 0.5, that's just the mean. So we're going to divide that by 0.5, which is the same as multiplying it by 2. And so correct to 3 decimal places, we get 0.547. Okay, part C. Using the model described on page 19, the transport company can make 46.48% of its deliveries over the interval -3 to 2. Okay, let's confirm that. Menu 552, -3 to 2. Okay, yep, correct. It has an improved delivery model with a mean of k and a standard deviation of 4 minutes. Okay, so standard deviation is going to stay at 4. We're going to shift the mean to be k. Find the values of k, correct to 1 decimal place, so that 46.48% of the transport company's deliveries can be made over the interval 4.5. Okay, it's just a straight solve for the mean with my cas. It's quite a lot of marks for that, so let's think about what we're going to write down. Let's just clarify some of the things we already know. So in fact, normally I would have back here, I know it told you everything, but I would have clarified that t is the variable that's defined for you. Yes, random variable t. T is a normally distributed variable with a mean of 0 and a standard deviation of 4, so that's variance that goes in that position, so we write 4 squared, or you could write 16. Probability of t being less than or equal to a is 0.6, and that therefore gave us a is approximately 1 minute. Okay, so, alright, I don't think we should need to write this again, but we've got 3 marks worth of things to earn. Let's clarify again that, no, actually, sorry, we don't want that. Let's do our new t. So let's make it, so Tn is new time taken, new delivery time. Tn is a normally distributed variable. This time we don't know the mean. Mean's going to be k, sorry, let's use variables consistent with the question. And the standard deviation is 4, so 4 squared. Okay, we want the probability of t being between negative 4.5. Now, personally, it's variable t, and 0.5 to be 0.4648. Okay, so we're going to be solving a normal distribution, so menu 552, negative 4.5 to 0.5. Mean is what we don't know. It's going to be k. We're going to solve for that. Standard deviation is 4. That's okay. Just doesn't like the unknown in the normal CDF. So we want that to be equal to this number we calculated up here. We're going to solve that for k. And that tells us that k is negative 1.5. I've just had a quick look at the examiner's report, and this is a really interesting one because only 6% of people earned 3 marks here. I think it was something like 17% earned 1 mark and 19% earned 2 marks. So most people got 1 or 2 of the marks here. I'm just interested, sorry, this should be variable tn, not variable t. I'm just kind of interested in, I think this might be an example of the exam setters not being aware of how straightforward this is to answer with your CAS. You know, it could have been worth 3 marks if they didn't give us this information. We could have found that information ourselves. There would have been a mark there in getting the 46.48 if we'd been told that with the probability of the new model being between negative 4.5 and 0.5 was equivalent to the old model being between negative 3 and 2, and find the value of k. I can see how there's 3 marks there, but having given us that bit of information, there's really not 3 marks worth of working here. And it's interesting, the examiner's report makes a comment on students are reminded appropriate working must be shown. They show a sort of integral calculation. They talk about translation, which, yeah, I mean, obviously we could use a graphical method here, but it's not required. So what we're being told, let's go back up to our graph, negative 3 to 2. So we're being given this information. So, oops, sorry. So we've been given the information that from negative 3 to 2, that area there is 0. Whatever it is, 4648. And I think what they want you to do is rethink the symmetry a little bit, in that this is the mean plus half a standard deviation, and negative 3, remembering our standard deviation is 4. This is the mean minus 3/4 of a standard deviation. And what do we want it to be between? Negative 4.5 and 0.5. We want that to be the same. So I think what they're essentially wanting you to do is sort of think through, firstly, the symmetry of it. So if we flipped this around and went from negative 2 to 3, obviously that's still going to be the same area, 0.4648. The only reason I've done that is because I think, oh, sorry, gone too far. The only reason I've flipped it around is because I think that this is very low down, and so I think we're going to want, I don't think the mean will go that low, so I think the mean's going to need to be closer to the 0.5 than it is to the negative 4.5, so I think there's some symmetry here. Possibly, or possibly not, actually. So what do we want these to become? Sorry, negative, we want them to essentially become negative 4.5 and 0.5. And we know that the standard deviation is 4. Yeah, which essentially means that, yeah, so this is just the mean plus 2 and the mean minus 3, because the standard deviation is not changing. So this is the mean plus 2 and the mean minus 3. So actually, no, I don't think we need to flip it around at all. Ignore the orange. Yeah, and so really all we're saying is that if you solve that, if they're the same thing, if the mean plus 2 is 0.5, then the mean is minus 1.5. And the same should hold here. Mean minus 3 equals negative 4.5, so mean is negative 1.5. So I think they talked about a graph being valid working, but yeah, even then it's relatively straightforward. So yeah, I'm intrigued as to what they were expecting for 3 marks, and given that only 6% of students got 3 marks, I suspect that almost no one showed as much as what they would have liked to have seen, but it's, I think, a problematic question that they're setting a question and demanding working that is genuinely not required in order to answer this question. So anyway, we'll see. A rival transport company claims that there is a 0.85 probability that each delivery it makes will arrive on time or earlier. Assume that whether each delivery is on time or earlier is independent of other deliveries. Assuming that the rival company's claim is true, find the probability that on a day in which the rival company makes 8 deliveries, fewer than half of them arrive on time or earlier. Okay, so this is now a binomial situation. So we've got E is the number of on-time or early deliveries. So number of not late deliveries, I guess. E is a binomial variable. We're going to make 8 deliveries, I think it said. Yes, 8 deliveries on this day. So N is 8. And the probability that a delivery is on time or early is 0.85. Okay, so we want a probability that fewer than half arrive on time or earlier. So that is the probability that the number of on time or earlier deliveries is fewer than half of 8. So fewer than 4. Now, being careful about binomial, fewer than 4 means less than or equal to 3. Okay, and so menu 55B for our binomial CDF. Number of trials is 8, probability of success is 0.85, our lower bound is 0, and our upper bound is 3, not 4. Okay, and so that's going to be, what do we want, 3 decimal places? 0.003. Okay, part E, assuming that the rival company's claim is true, so we can still assume this same binomial distribution, although 8 might not be relevant here. Consider a day in which it makes N deliveries. Okay, so now we're going to change. It's still about E, the variable's still E, but now we have, for this question, E is a binomial variable where the number of deliveries is unknown, but we're still assuming their claim of the number of on-time/early deliveries is 0.85, or the probability of that. Express in terms of N the probability that one or more deliveries will not arrive on time or earlier. Okay, so not arrive on time or earlier. One or more deliveries will not arrive on time or earlier. So that means that, yeah, I think I need to rephrase my binomial variable just to make life easier. So I'm actually going to make it, I'm going to use a different variable this time. I'm going to say that L is the number of late deliveries, so that is not on time or early. L is a binomial variable where we don't know N, but 0.15 probability of a delivery being late. So that is not on time or earlier. i.e. will arrive late. Okay, so then we want the probability that one or more deliveries will arrive late. So probability that a number of late deliveries is one or more, which is 1 minus, now we want an expression involving n, so it's not just about using our cas here. So that's going to be 1 minus the probability that we get no late deliveries. So that is 1 minus, that's going to be n choose 0, 0.15 to the 0, and 0.85 to the n. And so that means we're going to have 1 minus n choose 0 is 1, 0.15 to 0 is also 1, so it's just 1 minus 0.85 to the power of n. Hence, or otherwise, find the minimum value of n such that there is at least a 0.945 probability that one or more deliveries will not arrive on time or earlier. Okay, so remembering not arrive, will arrive late. Okay, so that means I want the probability that one or more late deliveries being at least 0.95. Now, normally I would use inverse binomial n or a trial and error method here, but given I've been forced to set up this expression here, I'm just going to solve that equation with my cas. So menu 3.1, it's going to be 1 minus 0.85 to the power of n greater than, and again, I don't really love this question either, in that it forces you into a method that, you know, perhaps is not the best method to use for a finding n kind of question. So n is greater than 18.4, and so therefore obviously n has to be a whole number, so minimum value of n is 19. Okay, and so part F. An analyst, that's a tongue twister, an analyst from a government department believes that rival transport companies' claim is only true for deliveries made before 4 p.m. For deliveries made after 4 p.m, the analyst believes the probability of a delivery arriving on time or earlier is x, where x is between 0.3 and 0.7. Okay, so the probability of a delivery, so we don't know the probability this time. We're just estimating it somewhere between 0.3 and 0.7. So we're claiming that it was 0.85. The probability of a delivery arriving on time or early before 4 p.m. was 0.85. Now we're saying it's lower than that, and it's somewhere between 0.3 and 0.7 inclusive. Okay, after observing a large number of the rival transport company's deliveries, the analyst believes that the overall probability that a delivery arrives on time or earlier is actually 0.75. Okay, so now we're saying that it's more than 0.7. Okay. The first paragraph seems a strange statement to make. Let the probability that a delivery is made after 4 p.m. be y. I suspect this probability question got rewritten in a bit of a hurry because they had to take out a lot of the probability that students didn't know how to do. So I suspect that's why there's some slight things that I don't think are great about its phrasing or what they're expecting of you in terms of marks. Okay, sorry. So after observing a large number of the rival transport companies' deliveries, the analyst believes that the overall probability, okay, so that's both before 4 p.m. and after 4 p.m. Okay, so we need to think about a tree diagram situation here. So we have two things happening. Maybe that's not quite what I need to do, but this is where my head's going to start with. So before 4 p.m, after 4 p.m, early or on time or late. So we know that before 4 p.m. that was 0.85 and that was 0.15. And this is now what we don't know. That's x. let the probability of delivery is made after 4 p.m. be y. Okay, so that's 1 minus y up there. Okay, so we know the equation is going to come from the fact that we know the probability of a delivery arriving on time or earlier to be 0.75. So that is the delivery can be before 4 p.m. and on time or earlier, or after 4 p.m. and on time or earlier. Okay, so the probability that a delivery is on time or earlier is 1 minus y times 0.85 plus y times x, and we believe that that is 0.75. Okay, so I've got an equation involving x and y. Assuming the analyst's beliefs are true, find the minimum and maximum values of y. Okay, so it's a max-min problem, and I'm trying to maximize or minimize y, so I need to make y the subject of this equation that I've just created. So that's going to be 0.85 minus 0.85y plus y times x equals 0.75. I'm going to take away that 0.85, and I'm going to factor y out of these other terms. So I'm going to have y times, it'll be x minus 0.85, and then I'm subtracting that 0.85, so it's negative 0.1. Okay, so y is negative 0.1 over x minus 0.85. Okay, so we have this relationship between x and y. It's a hyperbola translated to the right by 0.85 and reflected and not up or down. So we're essentially going to have, if that's 0.85, let's put it right over here. Reflected means it'll be in these two quadrants. Okay, but remember, we also have a domain. We know that x is between 0.3 and 0.7. Okay, so what we need to think about, was that inclusive? Yes. Is 0.3 to 0.7 is actually all we're interested in. So we know minimum value of y occurs when x equals 0.3. So min y is going to be negative 0.1 over 0.3 minus 0.85. So that is going to be negative 0.1 over 0.3 minus 0.85. Okay, so we actually want that to be exact, so 0.3 minus 0.85. Okay, so this is actually negative 0.1 over negative 0.55, which means it's 10 on 55. 5 is a common factor there, so 2 on 11. And maximum value of y is going to be when x equals 0.7. So we're going to have, okay, so that's minus 0.1 and negative 0.15. So that's going to be 10 on 15. And so the maximum value of y is 2/3. Okay. Alright, so I had this happen before with the paging. Hopefully that'll resolve itself in a second. There we go. Question 4. The graph of the function f of x equals blah 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 is shown below. Okay, let's define that function. Defining f of x equals 2 times x times, making sure we're using proper e to the power of 1 minus x squared. X is between 0 and 3. I never define functions with domain restrictions. I find they can create all sorts of problems when you're trying to do things with the function. We just always have to remember that domain and only take the solutions from that domain. Find the slope of the tangent to f at x equals 1. Okay, slope of the tangent to f at x equals 1 is just the derivative of f at 1. So that's going to be shift minus derivative of f oops, sorry, is that, and we want the derivative of f at x equals 1, and so it's going to be negative 2. Find the obtuse angle that the tangent to f at x equals 1 makes with the positive direction of the horizontal axis. Okay, so at x equals 1, it's got a negative gradient, so it must be on this side. So let's say that's 1 there. So we're saying that's got a gradient of negative 2. Okay. We want the obtuse angle that that line I've just drawn in, that tangent, makes with the positive direction of the horizontal axis. Obviously, x-axis is the horizontal axis, so that is the angle that I'm trying to find there. So we know that tan of that angle is, now you always need to be a little bit careful about the negatives. So what I would actually probably do is just, you either do tan theta equals 2, but it's going to give you the acute angle, okay? Or if you do tan theta equals negative 2, it will give you this negative angle going this way. Okay, so you just need to be a bit careful about how you phrase it. So I might actually not call it theta, I might just say tan of some other unknown angle is going to be negative 2. So that's a property of gradient. Tan of the angle, of the acute angle that it makes with the x-axis is equal to the gradient. You just have to be a bit careful about the negative though. You'll get a negative angle here. You have to be a bit careful about how to interpret that. So that means that this angle is inverse tan of negative 2. Sorry, so if I do inverse tan of negative 2, oops, control enter, all in degrees, to the nearest degree. So we change our mode of our CAS into degrees. Let's do that again. Okay, so this is negative, what do we want, to the nearest degree? Negative 63 degrees. Okay, so that is actually that angle there. The negative is just sort of telling me that it's under the x-axis, and so therefore the obtuse angle theta is going to be 180 minus 63, and so it's going to be 117. Okay, part C, find the slope of the tangent to f at a point x equals p. Give your answer in terms of p. Okay, so it's just the gradient at p. Alright, so one thing I often like to do is actually define a gradient function. It just makes it much easier to work with. So I'm going to define the derivative of f as df of x. I use the same convention every time. And define that as the derivative. And so then that makes it easier for me to substitute p into that derivative, which gives me that. So it's going to be 2e minus 4e p squared times e to the negative p squared, which is a really weird way of writing that. I find the CAS does really weird things in terms of unnecessary factorization. No, sorry, I was thinking that was e to the p squared there, so they were going to cancel that. So yeah, it's not very nice either way. But we could write it all over e to the p squared, however you'd like to write it. So we could choose to write it as 2e minus 4e p squared over e to the p squared. You might also choose to take out the 2e and have it as 1 minus p squared over e to the p squared. So all of those would be perfectly correct answers to this. Okay, part D. Find the value of p for which the tangent to f at x equals 1 and the tangent to f at x equals p are perpendicular to each other. Okay, so we already know that the tangent to f at x equals 1 has a gradient of negative 2. So we now want to know where is there a gradient of positive 1/2, so that the tangents will be perpendicular to each other. Feels like that might not exist in this domain. Let me just read that again. Find the value of p. The tangent to f at x equals 1. Okay, that's the one I've already got drawn in up here. which we know is a gradient of -2, and the tangent to f at x equals p are perpendicular to each other. So that has a gradient of -2. So therefore, that is going to have a gradient of +1/2. Okay, so therefore we came up with an expression for the gradient up above. So we want that derivative at p to be equal to 1/2. So we're going to solve this derivative at p equals 1/2 for p. And we want 3 decimal places. We also need to be in the domain. So remember, our function only exists from 0 to 3, so p can only be a point somewhere within that domain from 0 to 3. And so therefore we're going to find that p is approximately 0.6, 3 decimal places, 655, since p is somewhere between 0 and 3. So I always acknowledge that sort of thing, the domain, if I'm ignoring a solution. So there are 2 solutions to that equation, but only one of them is relevant because of the domain. Hence, find the coordinates of the point where the tangents of the graph, where the tangents to the graph of f at x equals 1 and x equals p intersect when they are perpendicular. Okay, so therefore we're going to have another perpendicular tangent has a gradient of +1/2, which, as I said, my diagram's not very well drawn here. But yeah, it's going to be up here, isn't it? So we've got that sort of thing happening, where that gradient is 1/2, so therefore these are perpendicular. That therefore is p. Okay, and we now want to find, there's a lot of words here, but I don't think it's very complicated. Find the coordinates of the point where those 2 tangents that we've got drawn there intersect when they're perpendicular. So we just want to find the coordinates of this point of intersection, which means we're going to need to find the coordinates of those 2 tangents. It's not just going to be halfway between, because those gradients aren't symmetrical, so we'll need to find those 2 tangents. Okay, so tangent at x equals 1. So remember, it's when they're perpendicular, and we already know when they're perpendicular, p is that value, so we're going to be using that value for p. So the tangent at x equals 1, menu for 9 for tangent to f of x when x equals 1. Okay, so it's y equals 4 minus 2x, and we want the tangent at x equals that, 0.655. We know it's going to be y equals 1/2 x and then plus something. So I'm going to try to see how this will go exactly. Let's see how we go. Menu for 9, tangent line to f of x, comma, when x equals this number that I worked out up here. So I'm going to take that, I'm going to change the p to an x. I'm going to get rid of that solution that we don't want. Okay, so you can see that's actually accurate enough that it has told me it's 0.5. So it's going to be 1/2 x plus 1.991. Sorry, plus 1.991. Okay, so we want the point of intersection. So I'm going to solve those 2 equal to each other. 4 minus 2x equals 1/2 x plus 1.991. So in my CAS, I'm going to be solving that equals that for x. And we want 2 decimal places, so that gives us x is 0.80 to 2 decimal places. And obviously we want to substitute that back in. So y is going to be 4 minus 2 times 0.8. So I'm subbing that back into this nicer tangent up the top here. So we're going to have 4 minus 2 times that number there. Let's get rid of the x equals. And so y is approximately 2.39 to 2 decimal places. So therefore the coordinates of that point are 0.80 and 2.39. Okay, so slightly unusual for VCAA to ask you to round a decimal to 2 decimal places if it means giving 0.80. You do need to write the 80 though, otherwise if you omit that, your implication is that that value is exactly 0.8 and it's not. It just rounds to 0.80 when we go to choose 2 decimal places. If we went to 3 decimal places, it would be 0.804. If we went to 4 decimal places, it would be 0.8035. Okay, so 2 decimal places, even if the second decimal place is 0, unless the answer is exactly 0.8, you still need to write the 0. In my experience, I think they generally try to avoid asking you to round a decimal to a value that's going to have a 0 in the end. It's sort of not the right number of decimal places for that value. I don't know why they didn't just ask for this point to 3 decimal places and it would have avoided that problem. I feel like it's a little bit of a trick. Well, not a trick, but they're trying to trip people up rather than test the maths. I don't love that bit. Okay, 2 line segments connect the points 0 if at 0, okay, so that's just 0, 0, and 3 if at 3, okay, that's just 3, 0. Oh, actually, is it? Hang on, if at 0, I don't think there's an asymptote there, so this one's definitely 0, 0. Let's just check f at 3. Yeah, so that's not 0, that's just very small. So that's 3 times 6e to the negative 8. So that's going to be, it's a very small number, which is why it looks close to the x-axis, but it's not. Well, it is, but it's not on the x-axis, I mean. So we're going to connect those 2 points to a single point Q, which has an x-coordinate of n and therefore a y-coordinate of f at n. And obviously n has to still be in this domain from 1 to 3. The first line segment connects the point 0 if at 0 and the point Q. Okay, so that's, yep, this point. Let's just label these points, it makes it easy to talk about them. Let's make that O, let's make this P. So find the equation of this line segment in terms of n. Okay, so we're finding the equation of this line segment is the line segment OP. This is what I mean, I don't love this exam. There's unnecessary words here where if you set questions up, sorry, not OP, OQ. If you set questions up better, you could phrase the question better. So we're finding the equation of the line segment OQ. Okay, so we need gradient, which is going to be just rise over run, so it's just going to be f at n over n. So gradient is f at n over n, so that is f at n, oops, sorry, on n is just going to be that, 2e to the 1 minus n squared. Actually, let's just put f at n here, so this is n 2n e to the 1 minus n squared. Okay, so that's my gradient, and the y-intercept is clearly 0, and so therefore the equation of OP, won't put that there, the equation is going to be the gradient, times x, obviously plus 0. Okay, sorry, I just had to pause the video there, so I'm just resuming the recording. Okay, so we've just found the equation of the line segment OQ, so we've found this line here, the yellow one, okay, that's this, and then the next part is asking us to find the equation of this line here in part 2. So this is going to be ugly, so the gradient of this is obviously going to be f at n minus f at 3 over n minus 3, or you could write that as f at 3 minus f at n over 3 minus n. It'd be the same thing. And we obviously don't know the y-intercept here, so we're going to have to use find the equation. So I'm going to use gradient intercept form, which I've got drawn up here. So I'm going to put the gradient, which is that expression that I've just got there, and a point, the x and the y coordinate of the point there. So that means my equation of the line PQ, we're doing this time, is going to be, oh, actually no, sorry, let me leave that for a minute. Get to that in a minute. So we're going to have y minus the y coordinate of a point, so I'm going to use f at 3 equals the gradient, which is this expression I've just drawn over here, f at n minus f at 3 over n minus 3 times x minus the x coordinate of that same point. So we need to use 3. So that's the equation of the line. So y PQ is going to be equal to, I'm just going to leave it written like that. I've had a look at the examiner's report and it's perfectly fine to do so. The expressions, when you work them out and expand them all out and try to then copy them all out, there's high risk of transcription error. The minimal amount of space they've given to me here suggests that that's not required, and the examiner's report certainly confirms that an answer similar to either version that I've got written here is correct. Obviously, it does need to be an equation, so y equals or an equal sign in it somewhere. That first version is actually correct for the mark. But as I said, even if you just worked out that gradient, f at n minus f at 3 over n minus 3, that's the gradient, let alone by the time you then expand that out with x minus 3 and then add f at 3 on. So I'm just going to leave it like that, and that's fine. Okay, so then we want to find the value of n, where n is somewhere between 1 and 3, if there are equal areas between the function f and each line segment. Okay, so essentially we want these two grey areas shaded up here to be the same. Now, that's going to mean setting up some ugly integrals with these ugly equations, but actually, given they're straight lines, it's going to be just a bit more efficient in terms of what I write for me to use the triangles that I've got sitting there. So as you said, this distance along the bottom here is n, this vertical height here is f at n, this distance along the bottom here will be 3 minus n, and so as triangles they're going to be quite nice. So the first grey area is going to be the integral of the function from 0 to n, and then take away the triangle, this yellow triangle defined by that yellow straight line, and then the other area will be the green triangle, take away the integral of the function from n to 3. Okay, so I'm going to have integral from 0 to n of f at x minus that first triangle, so area of a triangle, half times base in this case, which is n, times the height, which is f at n. And that's going to be equal to the green triangle, which is half times the base times the height, which is also f at n, and then minus the integral from n to 3 of f at x. Okay, so we should be able to solve that. Let's see how we go. So menu 3, 1. Using the triangles is also going to make it more efficient to enter this expression in to my cas. So integral from 0 to n of f at x, f of x, with respect to x, minus half times n times f at n, and that has to be equal to half times 3 minus n times n, times f at n. Take away the integral, shift plus, from n to 3 of my function. dx. And then we want to solve that equation for n. We know n is between 1 and 3, but let's just, solve that. Now I just realized I've made an error here, and I've made an error that is because I paused the solution beforehand. I'd recorded this question previously and I wasn't recording. When I did it with using the equations of the tangents, and it was ugly, but it got me to the right answer. And then when I had a quick scan of the examiner's report, I saw, they just use triangles, that's really easy. But we need to be really careful about this, because this green area that I've just coloured in here is not actually a triangle, it's a trapezium, because remember, this isn't the x-axis here. So we need to be a little bit careful about that. There's a very tiny edge here that is this height that we need to think about here. So area of a trapezium is half times a plus b, which is the two parallel lines, which will be f at n and f at 3 times the perpendicular height of the triangle, which will be the 3 minus n. So perpendicular, I mean that direction there. So this horizontal distance is actually the height of the trapezium. So if we draw a trapezium this way, this is the height because it's the perpendicular distance between the two parallel sides. And so in this case, that would be 3 minus n. So in this case, I haven't quite got this right. So let me edit this. You could, of course, use your equations of the tangents, and I suspect that was a much more common solution. It was certainly my first instinct. It's just on the re-record I was trying to avoid having to write out those tangents again. Although interestingly in the solution there was a statement that students are discouraged from writing out the expressions again. The problem I have is that the tangents don't actually have official names, and so I called them YOQ and YPQ, and in the examiner's report they call it Y1 and Y2, but generally speaking, I would say if it's not an f of x or a g of x, I wouldn't be using that. I would be writing out the expression. So yeah, look, I think they certainly didn't expect you to write out the expression, but yeah, it would have been my instinct to write it out. So it's my instinct to try and avoid it, and now I've made a mistake by assuming a triangle when it was in fact a trapezium. So there's my a plus b in my trapezium, that's my height. Okay, so now let's try editing. It only makes a very, very slight difference because obviously that green area is very close to being a triangle because that f at 3 is very, very small. But it's not quite right. So let's edit this here. So this part here should be f at n plus f at 3. Let's see if we go. Okay, great. So that's going to give us n is approximately 3 decimal places 1.088, and that is because we ignored the smaller solution because the question told us that n is between 1 and 3. Okay, and the final question of the paper, question 5. So we have two functions, f and g. Let me just clear some things here. We define a new function. You don't need to clear f to redefine f of x. I'm just trying to tidy things up and get rid of any other variables I might have accidentally defined. As you can see, we're using a and b here, so clearing a to z will just make sure that if I've previously defined a as something, it's no longer an issue. So defining f of x as x cubed minus x, and g of x is the tangent to the graph of f at x equals a. Okay, so that means I can do that. I can also define g of x as being, menu 4.9, the tangent to f of x at x equals a. Actually, it won't be, it won't be g of x, it will be g of a. Oh no, it won't, it will still be, it'll be a tangent line, so it'll be mx plus c, there'll be an x in it, it's just the m and the c values will have a's in them. Okay, so if I want to see, just to make sure what's happening there, so there's my equation of the tangent, which we could have found in more steps than that, but we don't need to. Although, a show that might mean we do. Let's see where we are. So let B0 be the x-intercept of the graph of G at A. Show that B equals that. Okay, so therefore I actually think we probably need to show how to arrive at the equation of the tangent and then show how the x-intercept of the tangent is this particular value. So therefore I think we need to do a little bit of work by hand here. So let's do f, the derivative of f, because we'll need gradient of the tangent. That's going to be 3x squared minus 1. The derivative of f at x equals a is 3a squared minus 1. Oops, sorry, minus 1. And that's the gradient of my tangent. Okay. And so the equation of my tangent is going to be y minus the y coordinate, which will be f at a, equals my gradient of my tangent times x minus my x coordinate, which is a. So that is going to be y minus f at a is a cubed minus a. Gradient of the tangent is 3a squared minus 1 times x minus a. Okay, so the equation of the tangent, actually we don't even need to simplify it really. We can just say, so this here is the tangent. Let me just move this down. Okay, so then for x-intercept, we're going to let y equal 0. So we're going to have 0 minus a cubed minus a equals 3a squared minus 1 times x minus a. And we want to solve that for x, so let's tidy things up a little bit now. So we're going to have a minus a cubed on the left-hand side here. We're going to have 3a squared minus 1 times x minus 3a cubed plus a. Okay, let's collect those a terms onto the other side. So I'm going to add 3a cubed, which is going to mean I get 2a cubed. And I'm going to add a, which will cancel with that a. Sorry, subtract a, which will cancel with that a. And that equals 3a squared minus 1 times x. And so therefore x is equal to 2a cubed over 3a squared minus 1. Okay, and so that's the x-intercept, which means that b, which is the x-intercept, is going to be that. Now, actually, I probably just could have made that working a little more seamless by perhaps back here at the beginning, substituting the point b0. And so then I would have had b in it right from the beginning, and I would have got to my answer, but that's fine. Okay, so we've shown that b is equal to that as required. State the values of a for which b does not exist. Okay, so obviously we have a fraction here, and so the denominator of a fraction can't be equal to 0. So 3a squared minus 1 cannot equal 0, which means that a squared cannot equal 1/3, and so therefore a cannot be plus or minus the square root of 1/3, which means it cannot equal, that's a complicated chain of equalities. I'm going to be a bit careful about that. So we could say that. We could say a cannot equal, we'd probably write that as plus or minus 1 on root 3, or rationalised would be plus or minus root 3 on 3. Okay, I'm just going to rephrase the question slightly. So the values of a for which b does not exist is not a not equal to that. So the values of a for which b does not exist is a equals those values. So I'm just going to rephrase the whole calculation. Okay, so it does not exist for the solutions of that equation. State the nature of the graph of GA when B does not exist. Okay, so let's go back to what B is. So B is the x-intercept of GA, which is the tangent at A. So if B does not exist, there's no x-intercept for the tangent, and the only time there's no x-intercept for the tangent is if the tangent is parallel to the x-axis, and therefore it's a horizontal line. And so therefore that would be when we have stationary points. State the nature of the graph of GA when B does not exist. When B does not exist, GA, so GA, remember, is the tangent, is a horizontal line. Okay, D part 1, state all values of A for which B equals 1.1. Give your answer correct to 4 decimal places. Okay, so it's just a simple solve. So 1.1 equals 2a cubed on 3a squared minus 1. Let's get our CAS to solve that. 2a cubed, 2a cubed on 3a squared minus 1, and we are solving for a. State all values of A correct to 4 decimal places. Okay, so we're going to have A is approximately. Do we have any restriction for A previously? No, A is just a real number. Okay, so A can be any of these. Negative 0. We want 4 decimal places. 5052. 0.8084. Let's scroll across here. And 1.3468. Okay, the graph of f has an x-intercept at 1, 0. State the values of a for which b is between 1 and 1.1. Okay, so remember what we're looking at here. Let's stay focused on what we're dealing with here. So this is a cubic with an x-intercept at 0 and x-intercepts at plus and minus 1. So it's a positive cubic. That's what it looks like. Okay. GA is the tangent at any point. Okay. So at point A, sorry, when x equals A, we're drawing the tangent. Okay, so it can move around all over the shop. B is the x-coordinate of the tangent. Okay, so wherever the tangent crosses the x-axis is B. So let's just think through what we have happening here. So I have got, I'm just going to draw that diagram a bit bigger. A cubic function. Okay, I'm drawing tangents to that cubic function, so I'm going to draw it in a slightly different place where I can label everything a bit better. So tangent at A, okay, so this is y equals f of x, this is y equals GA of x, and then the x-intercept of that tangent is B. Okay, so that's what we have happening here. So we want to state the values of A for which B, that is the x-intercept of the tangent, is somewhere between 1 and 1.1. Okay, so this is negative 1 here. This x-intercept of this graph is 1 here. So we need the tangent to be, sorry, the x-intercept of the tangent to be out there past 1. Okay, so that's going to have to happen when certainly when A is somewhere past this second turning point. Okay, if A is somewhere in here, the x-intercept is not going to be happening out here past 1. And if A is somewhere over here, the x-intercept is certainly not going to be happening out past 1. So we know that A definitely has to be past the turning point. Okay, so we know if we know, actually we've already worked out those values, haven't we? We know that when A equals positive root 3 on 3, that's when we have a horizontal tangent, so that must be the turning point, so that must be root 3 on 3. So therefore A is going to have to be bigger than that to get the tangent to have an x-intercept out here, but obviously we need to work out what does the value of A have to be so that the tangent, sorry, let me draw that back again, so that the tangent doesn't go past 1.1. Okay, so we need to work out that this value has to be less than 1.1. So we've already got our expression for B. So our expression for B is 2a cubed over 3a squared minus 1. And we know that that's going to have to be within between 1 and 1.1. So let's solve that. I'm just going to edit this one here. I'm going to solve. So this time we need 1 is less than or equal to that expression, which has to be less than 1.1. And state the values of A for which. Okay, so obviously we've already thought through that A is going to have to be bigger than root 3 on 3, definitely. So we're definitely not interested in this interval here with negative values. So we're definitely going to want this other one. Let me just check what the size of, root 3 on 3 is about 0.6, right? And so therefore this second interval here, which is from 0.8 to 1.3, definitely makes sense given what we've seen in the diagram. So this would mean that A has to be, no, what, 3 decimal places, so 0.808 has to be less than A, which has to be less than 1.347. Okay, the coordinate B0 is the horizontal axis intercept of GA, yes. Let GB be the function representing the tangent to the graph of f of x at x equals b. Okay. Find the values of A for which the graphs of GA and GB, where B exists, are parallel and where B doesn't equal A. Okay, so therefore what we want is the gradient at A has to be the same as the gradient at B. So we need f dash at A has to be the same as f dash at B. And we already have another relationship between A and B, so we can make some simultaneous equations. So we also know that B equals 2A cubed on 3A squared minus 1. And so we should be able to solve those equations simultaneously. Now I'm just going to go back a second because I just realized, I've just checked the examiner's report, and I've just realized that actually there was no reason to omit those negative solutions from back over here. Yeah, so there's also a small window, sorry, I didn't think this through properly. There's also going to be a small window somewhere here where that tangent's going to hit in the right area as well. And so actually these negative A values up here, sorry to backtrack, these are also going to be correct. So we can have that interval, or we can have this interval, negative 0.505 less than A less than or equal to negative 0.5. Okay, be careful about how you write that notation. So it's a union or an or, not the word and. If you used and, there is no, that means intersection, and there is no intersection between those two sets of A values. So my apologies for making that assumption. Okay, so let's go back to here. So we've got our simultaneous equations. Let's see how we go solving those. So we're going to have menu 371 for our simultaneous equations. We're going to have two equations. The unknowns will be A and B. Oh, sorry. So our first equation is that the derivative of f, which I've previously defined df as just generically being the derivative of f, so I can use that. Derivative of f at A is going to be the same as the derivative of f at B. And then we also know that B is equal to 2A cubed over 3A squared minus 1. Okay, so we need to be a little bit careful about how we read this here. We've got A equals negative 1 and B equals negative 1, but we know that B can't equal A. Okay, so that solution is where B equals A, so that's not correct. We have A equals negative root 5 on 5 and B equals root 5 on 5. Okay, so there's the solution. So we get A equals negative root 5 on 5 and B equals positive root 5 on 5. That's one solution. Or let's see if there's another one that's valid. Okay, or we get A equals positive root 5 on 5 and B equals negative root 5 on 5. And then the final solution is A equals 1 and B equals 1, but again, we have this condition that B can't equal A. And so there are two possible combinations of what could happen. And then I've just done a quick reread of the question before I go on. Find the values of A for which, okay, and so therefore it is A equals plus or minus root 5 on 5. Okay, let P be some other function. Let's define P of X in our CAS. Define P of X equals X cubed plus W times X. W is a real number. Okay, show that P of negative X equals negative P of X for all W. Okay, so to show that, so we just need to do the algebra here. So, and we're being asked to essentially show that P is an odd function. This is the definition of an odd function. So we start with one side of the equation, so the left-hand side is P of negative X, which means negative X cubed plus W times negative X. Don't be stingy with the show that steps here, otherwise it's quite a trivial thing. So that is the same as negative X cubed. That is the same as minus WX. And then we can factor out the negative, so it's X cubed plus WX. And therefore what we have there is negative P of X, which is the right-hand side. Okay. A property of the graphs of P is that two distinct parallel tangents will always occur at Tp of t and negative Tp of negative t. Okay, so what we're doing here is generalizing what we saw happen previously. So what we've essentially now got is a function where, again, if we factorize that, that's x, it's going to be x squared plus w. And so we're going to get x-intercepts at 0 and plus or minus root negative w. So we're going to have a cubic similar to what we had before. It's positive. Okay, so it's going to be square root of negative w and negative square root of negative w. Now, I know we can't square root a negative, but that just must mean that w is going to have to be something positive. Or if it isn't, then those x-intercepts don't exist, and we only have the x-intercept at 0. So we have some sort of point of inflection happening there. So a property of the graphs of P is that two distinct parallel tangents will always occur at Tp of t, and okay, so again, there's going to be some symmetry going on where if this is t and this is negative t, the tangents at each of those are going to be parallel. Okay, which is what we saw happening up here. So it's a generalized version of what's happening here, where this is going to be t and this is going to be negative t, and this therefore is square root of negative w, and this is negative square root of negative w, and that's the situation we're looking at. So find the values of w such that a tangent to the graph of P at Tp of t for some t greater than 0 will have an x-intercept at negative t. Okay, so yes, there'll be a tangent somewhere over here. Just let me draw something in. There'll be a tangent somewhere over here which will intersect at negative t. Okay, so let's get a generic equation for the equation of the tangent. Okay, so let's do menu for 9. We're going to do tangent to P of X at x equals t. Okay, so tangent at x equals t is y equals negative 2t cubed plus 3t squared times x plus wx. So if we'd done that by hand, that would have had that x factored out. So we could write it that way if we wanted. So that would be the same as 3t plus w times x. And so the tangent will have an x-intercept at negative t0. Okay, so we're going to substitute that point in. When x equals negative t, y is going to equal 0. So y equals 0 when x equals negative t, sorry. And then we should be able to solve that for w. Okay, so let's solve menu 3, 1. I'm just going to take that. Obviously I need to make all the x's negative t's. And solve it equal to 0 for w. Okay, so we get that w equals negative t squared, or t greater than t equals 0, but we know that t has to be greater than 0. That's given to us in the question, so we can ignore that one. So w equals negative 5t squared. Find all values of w such that a tangent to the graph of p of t will have an x-intercept. Okay, so we'll have an x-intercept if w equals negative 5t squared. And since t has to be bigger than 0, if t is bigger than 0, so that means we're looking at here, t is bigger than 0, t squared is then bigger than 0, multiplying that by negative 5, that means that w will be less than 0. Oops, sorry, t squared. Sorry, got myself in an undo loop. Okay, so part H is a matrix transformations question, but it's really about the transformations, so we could, for the modern day, rephrase this information to say the transformed point xy is mx plus h and ny plus k. So it's just about thinking about m, h, n, and k. So m is multiplying the x coordinate, so that's therefore a dilation from the y-axis. N is multiplying the y coordinate, so that's therefore a dilation from the x-axis. H is translating left and right, and k is translating up and down. So then we need to state any restrictions on the values of m, n, h, and k. And I think this should probably say m, n, h, and or k. Given that the image of P under the transformation T always has the property that parallel tangents occur at... Okay, so the transformation T is anything, okay? So it's basically saying, can we do any transformations that we want to P of X and still get this property that we've got happening here? So where we get this nice, and I know this graph has gotten a bit ugly, but again, let's go back. Let's remember we've got this lovely, nice symmetry where, it's not quite symmetry, let's try again. Where if I pick a point over here at negative t, and therefore the same point over here at positive t, and I draw the tangent at that point, those two tangents will be parallel. Okay, now we need to think about what could we do to the graph. So if we dilated this graph from the x-axis, so that is we stretched it away from the x-axis by the same factor in both directions, the gradients of those tangents would change, but they would still be parallel. Okay. Similarly, if we dilated the graph from the y-axis, so we stretched it out this way, okay, the gradients of those tangents would change, okay? If we stretched this graph out further, the gradients of the tangents would change, but they'd still be parallel. Okay, so I don't think there's any dilations that would be problematic. So I don't think there's any restrictions on M and N. H and K, so again, if we translated this up and down, let's do this in a simple way. So if I took that x-axis and moved it further down, that's not going to change the situation. Or moved it up here, that's not going to change the situation. So we can go up and down as much as we want. it's still going to be the exact same diagram and those tangents will still be parallel. Now the problem happens though, if we start to try and move left and right, if I move my x-axis over here, we no longer have this symmetry between negative t and t. Now, this isn't negative. If this is t here, negative t is way out over here. And so we don't have that symmetry property happening. So we definitely can't translate left and right. Oh, sorry. Trying to get my x-axis back. There we go. So we definitely can't translate left and right, or we're going to lose the whole symmetry thing going on here. So to me, there are no restrictions on m, n, or k. Okay. So no restrictions on m, n, or k. So the properties will still hold then. But h must be 0. Okay, so that's the only restriction. We can't translate left or right. Everything else, the property would still hold true. This question wasn't very well answered looking at the examiner's report, and I think students struggled with the fact that there was lots of variables here, m, n, h, and k, but there was only a restriction on one of them. They sort of tried to create restrictions on m and n and k when they didn't exist at all. I don't, to be honest, love the latter part of this question. I think things got a bit unwieldy when the concepts actually aren't that difficult. Just the sort of wording of everything got a bit ugly. But, you know, if you could think your way through that, they're not overly difficult questions. It was just working your way through all the sort of algebra happening here. The other thing to note here is this was sort of designed to help you, because what you're identifying up here is that p is an odd function, and so it's that really nice symmetry, that odd function symmetry, that actually means we get these parallel tangents. And so this will still be an odd function if we dilate it in either direction or if we translate it up or down, but it won't be an odd function if we translate it left or right, and so therefore that's where the problem arises. Okay, that was a long one. Apologies for that. I've recorded it over several different sessions as well, so I've lost sense of how long it's taken. But that is the solutions to the 2020 Exam 2, remembering that this was a modified study design with less probability. I also think that meant that there were some fairly last-minute changes had to happen to the exam to adjust for those study design adjustments. Now, they're not last minute, they're not in the days before, but it's a shorter timeline for setting an exam than what usually occurs. And so I think there were some issues in the probability question that I didn't love. But otherwise, you know, a reasonably fair paper.